Look up at the night sky and it feels endless. Galaxies stretch in every direction, light traveling for billions of years just to reach us. But here's the question that keeps astronomers awake at night. Are we living on the edge of the universe? Is there a boundary to everything we can see? A final horizon beyond which nothing can reach us? Or does the universe keep going forever while we sit inside a cosmic bubble of light? Today, we're stepping right up to that edge and finding out what it really means. The universe as we know it. The universe is not something we stand inside of and look at from a distance. It is the total stage on which every event has ever happened. Every particle, every force, every flash of light, every moment of time exists inside it. When scientists say the universe is about 13.8 billion years old, they are not guessing or telling a story. They are reading a record written in light, motion, temperature, and structure. The universe carries its own history in the way galaxies move apart, in the faint heat left over from its birth, and in the limits of how far we can see. Age in the universe is not measured the way age is measured for living things. There is no calendar, no ticking clock floating in space. Age is measured through expansion. When astronomers observe distant galaxies, they see that almost every galaxy is moving away from us, and the farther away it is, the faster it is moving. This pattern reveals that space itself is expanding. By reversing that expansion mathematically, scientists trace everything back to a time when all matter, all energy, and all space were compressed into an extremely hot, dense state. That moment marks the beginning of the universe as we know it. The 13.8 billion years is not an estimate pulled from theory alone. It is supported by multiple independent measurements, including the expansion rate of the universe, the oldest known stars, and the temperature of the cosmic microwave background. Size is harder to grasp than age because the universe does not have clear edges that can be walked to or seen directly. What we can measure is the observable universe, which is defined by how far light has had time to travel since the universe began. Light does not move instantly. It moves at a fixed speed, the fastest speed allowed by the laws of physics. Because the universe has existed for 13.8 billion years, light from regions farther than that distance has not had enough time to reach us. This creates a natural boundary, not a wall or an edge in space, but a horizon in time. Beyond this horizon, the universe may continue, but it is hidden from view. The observable universe is not 13.8 billion light-years across. Because space itself has been expanding while light travels through it, the most distant regions we can see today are now much farther away than when the light began its journey. The observable universe has a radius of about 46 billion light-years, making its full diameter around 92 billion light-years. This does not mean we are at the center in any special sense. Every observer anywhere in the universe sees a similar horizon centered on themselves. The observable universe is not a privileged location. It is a consequence of time, light speed, and expansion. Beyond the observable universe lies what scientists call the unobservable universe. This is not speculation in the casual sense. It is a logical result of the same physical laws we observe locally. The same matter, energy, and expansion that exist within our horizon almost certainly continue beyond it. There is no evidence that space suddenly stops or changes character at the boundary of what we can see. The universe beyond the observable limit is not a different place governed by different rules. It is simply beyond the reach of information. Inside the observable universe, matter is not spread evenly. It is organized into structures of increasing scale. The smallest large-scale structures are galaxies, massive systems made of stars, gas, dust, dark matter, and radiation bound together by gravity. A typical galaxy contains hundreds of billions of stars, each star potentially hosting planets, moons, and complex systems of its own. Galaxies come in different shapes, including spirals, ellipticals, and irregular forms. These shapes are not decorative features. They are records of how galaxies formed, collided, merged, and evolved over billions of years. Galaxies rarely exist in isolation. gravity pulls them together into clusters, which can contain hundreds or thousands of galaxies bound in a shared gravitational field. Galaxy clusters are among the largest structures held together by gravity. They are filled not only with galaxies, but also with extremely hot gas that emits X-rays, and with vast amounts of dark matter that cannot be seen directly, but whose presence is revealed through its gravitational effects. Clusters themselves are not randomly scattered. They form part of even larger patterns known as superclusters. These structures stretch across hundreds of millions of light years. Superclusters are not tightly bound objects like galaxies or clusters. They are looser associations shaped by the slow flow of matter through space under gravity. When mapped on the larger scales, superclusters and clusters form long filaments and walls, surrounding enormous empty regions called cosmic voids. This arrangement is known as the cosmic web. The cosmic web gives the universe a structure that looks almost organic, like a network of fibers and nodes. This pattern did not exist at the beginning. It grew over time. Tiny differences in density in the early universe were amplified by gravity. Regions that were slightly denser pulled in more matter, becoming galaxies and clusters, while less dense regions emptied out into voids. The universe did not start smooth and become chaotic. It started nearly uniform and became structured. One of the most important pieces of evidence for this early uniform state is the cosmic microwave background, often shortened to CMB. The CMB is not light from stars or galaxies. It is radiation left over from a time when the universe was hot enough that atoms could not exist. In the early universe, matter and energy were mixed into a dense plasma of charged particles. Light could not travel freely because it constantly collided with electrons. The universe was opaque. As the universe expanded and cooled, it reached a point about 380,000 years after the Big Bang, when electrons and protons combined to form neutral atoms. Once atoms formed, light was suddenly free to travel without being scattered. The radiation released at that moment has been moving through space ever since. As the universe expanded, this radiation stretched, cooling and shifting into the microwave part of the electromagnetic spectrum. Today, it fills the entire universe, coming from every direction with nearly the same temperature. The CMB is not perfectly uniform. Tiny temperature variations, on the order of 1 part in 100,000, are visible when measured precisely. These small differences correspond to the early density variations that later grew into galaxies and clusters. The CMB is therefore not just a glow. It is a detailed map of the universe when it was extremely young. It provides a snapshot of the universe at a time long before stars, planets, or galaxies existed. The temperature of the CMB today is about 2.7 degrees above absolute zero. This temperature is nearly the same everywhere, which shows that the early universe was remarkably uniform. This uniformity is one of the strongest pieces of evidence that the universe began in a hot, dense state and expanded rapidly. It also places strong limits on how the universe could have evolved, ruling out many alternative models. The CMB also defines the most distant surface we can observe directly. When astronomers look at the CMB, they are not seeing an object in space. They are seeing a moment in time. This surface is sometimes called the surface of last scattering, marking the boundary between an opaque early universe and a transparent one. Beyond this surface, light cannot reach us because it was trapped before atoms formed. In this sense, the CMB marks the edge of what can be directly observed using light. Galaxies formed long after the CMB was released. Over hundreds of millions of years, matter slowly gathered under gravity. The first stars ignited, producing heavy elements through nuclear fusion. These elements later became the building blocks of planets, atmospheres, and complex chemistry. Galaxies grew through mergers and accretion, evolving into the structures we see today. Even now, galaxies continue to collide and change, reshaping themselves over immense spans of time. The universe today is not static. It is still expanding, and that expansion is accelerating. Distant galaxies are moving away from us faster now than they were in the past. This acceleration is attributed to dark energy, a form of energy that appears to be inherent to space itself. Dark energy does not clump like matter. It acts uniformly, pushing space apart on the larger scales. While dark energy does not directly affect galaxies or clusters, it dominates the universe's behavior at vast distances. Despite this expansion, local structures remain intact. Gravity within galaxies and clusters is strong enough to overcome the expansion of space. This is why stars remain bound to galaxies, and galaxies remain bound to clusters. Expansion becomes significant only across immense distances where gravity is weak. Everything we know about the universe comes from interpreting signals carried by light, particles, and gravitational waves. We do not observe the universe as it is now, but as it was when the signals left their sources. Looking deeper into space is equivalent to looking further back in time. The most distant galaxies we can observe are seen as they were billions of years ago, when the universe was young and galaxies were smaller, brighter, and more chaotic. The universe as we know it is defined by these limits: the speed of light, the age of time, the expansion of space, and the distribution of matter and energy. Within these limits, we see a universe that began hot and dense, cooled as it expanded, formed structure through gravity, and continues to evolve. The observable universe is not the whole universe, but it is a vast and detailed region containing hundreds of billions of galaxies, each with its own history written in stars and motion. The cosmic microwave background remains the deepest direct view into the universe's past, a faint but precise signal that anchors all modern cosmology. Galaxies, clusters, and superclusters trace the growth of structure from near-uniform beginnings. The scale of the universe defies everyday intuition, stretching across distances so large that even light requires billions of years to cross them. Yet every part we can observe follows the same physical laws, showing no sign of special locations or preferred directions. The universe, as we know it, is not defined by what lies beyond observation, but by what can be measured, mapped, and tested. Its size is bounded by time and light, its age by expansion, its structure by gravity, and its earliest visible moment by the release of the cosmic microwave background. Within this immense framework, everything we see exists as part of a single, continuous cosmic system governed by the same fundamental processes everywhere it can be observed. Big Bang and cosmic expansion. The Big Bang was not an explosion in space. There was no empty darkness waiting for matter to burst into it. There was no center point where debris flew outward into a surrounding void. The Big Bang was the rapid expansion of space itself, happening everywhere at once. Every region of the universe was involved. Every point that exists today was once compressed into an extremely hot, dense state. Space did not expand into something else. Space expanded into itself. To visualize this correctly, imagine space as a grid rather than a container. At the beginning, the grid lines are incredibly close together, packed so tightly that distances are almost meaningless. As time moves forward, the grid stretches. The points on the grid move farther apart, not because they are traveling through space, but because the space between them is increasing. Galaxies do not race outward like shrapnel. They remain roughly where they formed while the distances between them grow. In the earliest fraction of a second after the Big Bang, the universe was so hot and dense that the known laws of physics cannot fully describe it. Matter and energy were indistinguishable. Forces that are now separate, such as electromagnetism and the nuclear forces, were unified. As the universe expanded and cooled, these forces separated and particles began to take on stable forms. This cooling was not a loss of energy into surroundings. There were no surroundings. It was a consequence of expansion, as energy spread over increasing volume. As space expanded, wavelengths of radiation stretched with it. This stretching is still happening today. Light traveling through the universe does not merely move across static distances. The distances themselves change while the light is in transit. This is why distant galaxies appear redshifted. Their light is shifted toward longer wavelengths because space expanded during its journey. Redshift is not caused by galaxies moving through space, like objects through air. It is caused by space itself changing scale. The relationship between distance and redshift led to one of the most important discoveries in cosmology. When Edwin Hubble measured the light from distant galaxies, he found a consistent pattern. The farther away a galaxy is, the faster it appears to be moving away from us. This relationship is known as Hubble's law. It is expressed simply: velocity is proportional to distance. Double the distance and the apparent recession speed doubles. Hubble's law does not mean that Earth occupies a special location. The same pattern would be observed from any galaxy. Every observer sees distant galaxies moving away, with speed increasing with distance. This is exactly what is expected in an expanding universe where space itself is stretching uniformly. The expansion rate of the universe is quantified by the Hubble constant, which describes how fast space expands per unit distance. Measuring this constant precisely has been one of the central goals of modern cosmology. Different methods, including observations of supernovae, galaxy motions, and the cosmic microwave background, all confirm expansion, though they reveal subtle tensions in the exact value. These tensions are not signs of error in the Big Bang model, but indicators that the universe contains components like dark energy that influence expansion in complex ways. If expansion is reversed mathematically, distances shrink, temperatures rise, and matter becomes increasingly dense. Following this backward leads to a state where the universe was once extremely small, hot, and uniform. This is the initial condition described by the Big Bang theory. The theory does not claim to explain why the universe began or what came before. It describes how the universe evolved from its earliest measurable state onward. Its strength lies in its predictions, which match observation with remarkable precision. One of the strongest confirmations of the Big Bang is the cosmic microwave background. This radiation is a direct result of expansion. When the universe cooled enough for atoms to form, light was released and began traveling freely. As space expanded, that light stretched, cooling into microwaves. The existence, temperature, and uniformity of the CMB are all natural consequences of an expanding universe that began hot and dense. Expansion also explains why the universe looks the way it does on large scales. In the early universe, matter was distributed almost evenly, with tiny density variations. As expansion slowed the overall density, while gravity amplified those variations, matter clumped into the structures seen today. Without expansion, the universe would have collapsed under its own gravity. Without gravity, expansion would have left matter too thin to form galaxies. The universe exists in a balance shaped by both. The idea of expansion raises a persistent and often misunderstood question. If the universe is expanding, what is it expanding into? And does this expansion imply an edge? The answer begins with understanding that expansion does not require an external space. Space itself is the entity that expands. There is no outer boundary that space is pushing against. There is no surrounding emptiness beyond the universe in which it grows. A useful visual model is the surface of a balloon. Imagine dots drawn on the surface. As the balloon inflates, the surface expands. Each dot moves away from every other dot. From the perspective of any dot, all others are receding. Yet the surface has no center within itself. The expansion occurs within the surface, not into the air around it. The balloon model is limited, but it captures the key idea. Expansion does not require an edge within the space being expanded. The universe may be finite or infinite. Expansion alone does not decide this. A universe can be finite and unbounded, like the surface of a sphere, or infinite and flat. Current observations suggest that the universe is very close to spatially flat, meaning its geometry does not curve strongly on the larger scales we can measure. A flat universe can be infinite, but it does not have to be. The observable region is finite regardless. The concept of an edge becomes clearer when distinguishing between a physical boundary and an observational limit. The observable universe has a boundary defined by the distance light has traveled since the beginning. This boundary is called the cosmic horizon. It is not a wall. It is not a location where the universe ends. It is simply the farthest distance from which information has reached us. Beyond this horizon, galaxies exist that are moving away from us so rapidly due to expansion that their light will never reach us, even given infinite time. This is not because they exceed the speed of light locally, which is forbidden, but because the space between us and them expands faster than light can cross it. This creates a permanent limit to what we can observe. This horizon can be thought of as an edge in a practical sense, but not in a physical one. Nothing special happens at that boundary. Galaxies beyond it follow the same physical laws as those within it. They have stars, planets, radiation, and structure. They are simply causally disconnected from us. The expansion of the universe also means that the observable region changes over time. In the early universe, the observable region was much smaller. As time passes, light from more distant regions reaches us, enlarging the observable universe. However, because expansion is accelerating, there are regions that will never become observable, no matter how long time continues. This acceleration was discovered through observations of distant supernovae. These exploding stars serve as standard candles, allowing astronomers to measure distances across billions of light years. The data revealed that expansion has been speeding up over the last several billion years. This acceleration implies the presence of dark energy, which acts as a repulsive influence on cosmic scales. The presence of dark energy changes the long-term behavior of expansion. In a universe without it, expansion would slow over time as gravity pulled matter together. With dark energy, expansion accelerates, increasing the separation between distant regions at an ever-growing rate. This does not create an edge, but it does deepen cosmic isolation. The Big Bang model does not describe the universe expanding from a point in pre-existing space. Every region of space was compressed. Every location now was once extremely close to every other location. The expansion happened everywhere simultaneously. Asking where the Big Bang occurred is like asking where the center of the surface of the Earth is. The question assumes a structure that does not exist. When visualizing cosmic expansion, scale is essential. On small scales, such as within galaxies or solar systems, expansion is negligible. Gravity dominates, binding matter together. On large scales, across millions of light years, expansion becomes dominant. This separation of scales allows structures to exist within an expanding universe without being torn apart. The Big Bang theory remains the most successful model of cosmic origins because it explains expansion, background radiation, light element abundances, and large-scale structure within a single framework. It does not require an edge to function. It requires only time, space, energy, and consistent physical laws. Whether the universe is infinite or finite beyond observation remains an open scientific question. Expansion alone does not answer it. What expansion does establish is that the universe has a measurable history, a changing scale, and limits on what can be observed. The edge we encounter is not a physical boundary in space, but a boundary in information, defined by time, light, and the ongoing stretching of space itself. Galaxies and the cosmic web. As space continued to expand after the early universe cooled, expansion did not erase structure. It created the conditions for structure to appear. The universe moved from a nearly uniform sea of matter and energy into a place where gravity could begin to shape patterns. Expansion stretched space, but gravity quietly worked in the opposite direction, pulling matter together wherever it was even slightly denser than its surroundings. This slow competition between expansion and gravity is what gave rise to galaxies, clusters, and the vast cosmic architecture that fills the observable universe today. The first galaxies did not appear immediately after the Big Bang. For hundreds of millions of years, the universe was dark. There were no stars, no glowing galaxies, no visible light. Matter existed mostly as hydrogen and helium gas, drifting through expanding space. Tiny variations in density, left over from the earliest moments of the universe and visible today in the cosmic microwave background, acted as seeds. Where matter was slightly denser, gravity pulled in more material. Over time, these regions grew heavier and hotter. As gas fell inward under gravity, it began to collapse into the first stars. These stars were unlike most stars today. They were massive, extremely hot, and short-lived. When they ignited, they ended the cosmic dark ages. Their light flooded the surrounding space, and their death seeded the universe with heavier elements. These first stars gathered into early galaxies, crude and chaotic compared to modern ones, but unmistakably the ancestors of everything we see now. Galaxy formation was not a single event, but a continuous process. Small galaxies formed first, then merged with others through gravitational attraction. Collisions were common. When galaxies collided, their stars usually passed by each other without direct impact, but their gas clouds slammed together, triggering bursts of star formation. Over billions of years, repeated mergers built larger and more organized galaxies. Spiral arms, central bulges, and massive halos of dark matter emerged through this long history of interaction. Dark matter played a crucial role in this process. It does not emit light, absorb radiation, or interact through electromagnetism, but it exerts gravity. Long before visible matter collapsed into stars and galaxies, dark matter formed massive invisible structures called halos. These halos acted as gravitational wells. Ordinary matter fell into them, collecting at their centers and forming galaxies. Without dark matter, galaxies as we know them could not exist. As galaxies formed, they did not arrange themselves randomly. Gravity acted on the largest scales, shaping matter into a vast interconnected network. Galaxies gathered along immense filaments that stretch across hundreds of millions of light years. These filaments intersect at dense nodes where galaxy clusters form. Between them lie enormous regions almost empty of galaxies, known as cosmic voids. This entire arrangement is called the cosmic web. The cosmic web is one of the most striking features of the universe on large scales. When astronomers map the positions of millions of galaxies, the pattern becomes clear. Matter traces long threads, sheets, and walls surrounding vast empty spaces. This structure emerged naturally from the initial conditions of the universe, combined with the relentless pull of gravity acting over billions of years. Cosmic voids are not completely empty. They contain sparse gas, dark matter, and occasional faint galaxies, but their density is far lower than the cosmic average. Voids can span tens to hundreds of millions of light years. They are the expanding bubbles of the universe, regions where matter drained away toward denser filaments and clusters. As the universe expanded, voids grew larger and emptier, while filaments became thinner and more pronounced. Filaments are the highways of matter in the universe. Gas flows along them toward dense nodes, feeding galaxies and clusters. These filaments are not solid structures, but regions where matter density is higher than average. They glow faintly in certain wavelengths due to hot gas and are traced indirectly through galaxy surveys and gravitational lensing. Filaments connect everything, forming a continuous structure that spans the observable universe. At the intersections of filaments lie galaxy clusters, the most massive gravitationally bound objects in the universe. These clusters contain thousands of galaxies, vast clouds of hot gas, and enormous quantities of dark matter. They act as anchors in the cosmic web, pulling in material from surrounding filaments. The motion of galaxies within clusters reveals the invisible mass holding them together, providing some of the strongest evidence for dark matter. Zooming in from the larger scales brings us closer to our own cosmic address. Our galaxy, the Milky Way, is a large spiral galaxy containing hundreds of billions of stars. It spans about 100,000 light years from end to end, and is surrounded by a massive halo of dark matter that extends much farther. The Milky Way's spiral arms are regions of active star formation, shaped by density waves moving through its disk. The Milky Way is not alone. It is part of a small group of galaxies known as the Local Group. This group contains more than 50 galaxies, including the Andromeda Galaxy, the Triangulum Galaxy, and many smaller dwarf galaxies. The Milky Way and Andromeda are the two largest members, locked in a slow gravitational dance that will eventually lead to a collision billions of years in the future. The Local Group itself is part of a larger structure called the Virgo supercluster, a vast region of space containing thousands of galaxy groups and clusters. This supercluster stretches across more than 100 million light-years. It is not a tightly bound object, but part of an even larger flow of matter toward massive regions of gravitational influence. From this perspective, Earth occupies no special location. We are not near the center of anything meaningful on cosmic scales. We are embedded in a galaxy, within a group, within a supercluster, woven into the cosmic web, like a single knot in an immense fabric. The same patterns that shape distant galaxies shape our own environment. As astronomers look farther into space, they also look further back in time. Distant galaxies appear younger, smaller, and more chaotic. Their shapes are irregular, their stars burn hotter, and their structures are less settled. This reveals how galaxies evolved over time, assembling piece by piece from smaller building blocks. The farther we look, the closer we get to the era when the first galaxies formed. Eventually, observation reaches a limit. There is a distance beyond which galaxies cannot be seen, not because they do not exist, but because their light has not had enough time to reach us, or because expansion has stretched their light beyond detectability. This boundary defines the edge of the observable universe. Beyond this boundary lies what can be called the surface of oblivion. This is not a physical surface or a barrier in space. It is a limit imposed by time and expansion. Light emitted from regions beyond this surface has never reached Earth and never will. Those regions are not dark in themselves. They contain galaxies, stars, and cosmic structures just like those we observe, but they are permanently disconnected from us. The surface of oblivion shifts over time. As the universe ages, light from more distant regions enters our observable horizon. However, because expansion is accelerating, there are regions moving away so rapidly that their light will never reach us. These regions cross beyond causal contact, disappearing behind a horizon created by expansion itself. This horizon does not destroy information. It simply places it beyond reach. The universe beyond observable light is not erased or diminished. It continues to evolve, form galaxies, and follow the same physical laws. The cosmic web likely extends far beyond what we can see, repeating its filamentary structure across distances that may be infinite. The idea of a surface of oblivion highlights a key feature of the universe. Visibility is not the same as existence. What we observe is a fraction of a much larger reality. The cosmic web does not end at the edge of observation. It fades from view as light fails to reach us, not because structure stops, but because time and expansion impose limits. Within the observable universe, every galaxy, filament, and void is part of a connected whole. Matter flows along gravitational pathways, shaped by the invisible scaffolding of dark matter. Galaxies evolve through interaction, collision, and slow transformation. Clusters grow by pulling in material from their surroundings. Voids expand as matter drains away from them. The Milky Way itself is shaped by these same processes. Its stars orbit within a dark matter halo formed billions of years ago. Its gas flows along spiral arms, forming new stars while older stars drift outward. Its satellite galaxies are remnants of past interactions, slowly being torn apart and absorbed. On the larger scales, the universe resembles a living network, constantly changing but governed by precise physical laws. The cosmic web is not static. Filaments shift, clusters grow, and voids expand as expansion and gravity continue their long interaction. This evolution unfolds over timescales far longer than human history, yet it leaves measurable traces in the distribution of galaxies and the motion of matter. The deeper astronomers look into space, the clearer it becomes that structure is a natural outcome of the universe's initial conditions and physical laws. There is no design imposed from outside, no organizing hand shaping galaxies into patterns. The cosmic web emerges from gravity, acting on tiny early differences, amplified across billions of years. As observation approaches its limits, the universe does not reveal an edge of matter or structure, but an edge of light. Beyond that edge, the cosmic web continues unseen, its filaments stretching into darkness, not because they end, but because the universe has grown too large and too old for their light to reach us. This unseen extension of the cosmic web defines the boundary between what can be known through observation and what remains forever out of reach. It is not a boundary in space, but a boundary in information, shaped by the history of expansion and the finite speed of light. Within that boundary lies everything humanity has ever observed. Beyond it lies a continuation of the same cosmic processes, unfolding silently beyond the surface of oblivion. Space and time. The fabric of the universe. Once galaxies, filaments and clusters take shape across the universe, a deeper question emerges beneath the visible structure. Matter does not simply float through an empty stage. The stage itself responds. Distances stretch, paths curve, and time flows differently depending on where matter and energy exist. To understand why galaxies move the way they do, why light bends, and why black holes form boundaries that nothing can cross, space and time must be treated not as separate things, but as a single interconnected fabric. Before the 20th century, space and time were thought to be fixed and absolute. Space was a rigid three-dimensional grid, and time flowed forward at the same rate everywhere. Gravity, in this view, was a force acting instantly across distance. This picture worked well for everyday experiences and even for planetary motion, but it failed when pushed to extremes. It could not fully explain the motion of Mercury, the behavior of light near massive objects, or the deep structure of the universe revealed by modern observation. Albert Einstein changed this picture completely with his theory of general relativity. Instead of treating gravity as a force, Einstein described it as a consequence of geometry. Space and time are woven together into a four-dimensional structure called space-time, and this structure is not rigid. It bends, stretches, and curves in response to mass and energy. Objects move the way they do not, because they are pulled by a force, but because they follow the natural paths created by this curved geometry. In this framework, space-time acts like a fabric. Where there is no matter or energy, this fabric is nearly flat. Where matter and energy are present, the fabric curves. The more massive or energetic an object is, the more strongly it bends space-time around it. This bending determines how objects move, how light travels, and how time passes. To visualize this, imagine a stretched sheet. Place a heavy object in the center, and the sheet dips downward. Smaller objects placed nearby will roll toward the heavier one, not because they are pulled directly, but because the surface is curved. In reality, the universe does not curve into a higher dimension the way a sheet does. But the analogy captures the key idea. Geometry replaces force. Einstein's equations describe precisely how matter and energy tell space-time how to curve, and how curved space-time tells matter and energy how to move. These equations are complex, but their consequences are clear and measurable. Planets follow curved paths around stars. Stars orbit within galaxies. Galaxies move within clusters. Light bends as it passes massive objects, creating phenomena such as gravitational lensing, where distant galaxies appear stretched, duplicated, or magnified. One of the most surprising aspects of curved space-time is its effect on time itself. Time does not pass at the same rate everywhere. Near massive objects, time flows more slowly than it does far away. This effect, known as gravitational time dilation, has been confirmed by experiments using precise clocks on Earth and in orbit. Even the global positioning system must correct for these differences to function accurately. Gravity is therefore not something added on top of space and time. It is a manifestation of their structure. When a planet or star moves, it is following the straightest possible path through curved space-time, a path called a geodesic. What appears as acceleration or attraction is simply motion along this curved geometry. This understanding becomes essential when examining extreme objects like black holes. Black holes are not just massive bodies. They are regions where space-time curvature becomes so intense that familiar concepts break down. When a massive star exhausts its nuclear fuel, it can no longer support itself against gravity. The star collapses inward. If its mass is large enough, no known force can stop the collapse. The result is a black hole. At the center of a black hole lies a region called a singularity, where density becomes infinite and space-time curvature becomes extreme. Current physics cannot fully describe conditions at this point. Surrounding the singularity is a boundary known as the event horizon. This is not a solid surface. It is a location in space-time where escape becomes impossible. The event horizon marks a fundamental boundary. Inside it, all possible paths through space-time lead inward toward the singularity. Even light, which normally travels at the maximum possible speed, cannot escape once it crosses this boundary. From the outside, objects falling toward a black hole appear to slow down and fade as their light is stretched and redshifted. From their own perspective, they cross the event horizon without noticing anything special at that exact moment. Black holes reveal that space-time can be shaped so strongly that it creates one-way regions. The event horizon is not an edge of space, but an edge of causality. Events inside the horizon cannot influence the outside universe. Information becomes trapped, at least according to classical general relativity. On cosmic scales, space-time curvature governs not only black holes, but the expansion of the universe itself. The overall geometry of space-time determines whether the universe is flat, open, or closed. Measurements of the cosmic microwave background and large-scale structure indicate that the universe is very close to flat on the largest scales we can observe. This means that, averaged over vast distances, space-time does not curve strongly in any direction. Despite this large-scale flatness, local curvature is everywhere. Stars curve space-time in their vicinity. Galaxies curve it more strongly. Clusters of galaxies warp space-time on even larger scales. These curvatures overlap and interact, creating a dynamic geometry that evolves over time as matter moves and structures form. Light traveling through the universe follows these curves. When light from a distant galaxy passes near a massive cluster, its path bends. This bending can focus light, making distant objects appear brighter or distorted. Gravitational lensing has become a powerful tool for mapping dark matter, revealing the invisible mass that shapes space-time without emitting light. General relativity also predicts gravitational waves, ripples in space-time produced by accelerating masses. When massive objects like black holes or neutron stars collide, they send waves traveling outward at the speed of light. These waves stretch and compress space-time as they pass. Their detection confirms that space-time is not static, but dynamic, capable of oscillation and motion. Time itself is inseparable from these effects. In strong gravitational fields, time slows dramatically. Near a black hole's event horizon, time relative to distant observers appears to almost stop. This does not mean time ends, but that its flow becomes extremely distorted. Space and time exchange roles inside the horizon, making movement toward the singularity as inevitable as moving toward the future. This merging of space and time into a single fabric reshapes how boundaries are understood. Black holes create boundaries that are not physical walls, but limits on communication and influence. These boundaries arise naturally from the geometry of space-time, not from added rules or constraints. On the larger scales, the universe itself contains horizons similar in nature. The cosmic horizon marks the boundary beyond which events cannot affect us, because space-time expansion prevents signals from reaching us. Like a black hole horizon, this boundary is defined by geometry and motion, not by material barriers. General relativity also explains why gravity becomes weaker with distance. not because it fades like a force spreading out, but because curvature becomes less pronounced. Far from massive objects, space-time approaches flatness. Motion becomes simpler, time flows more uniformly, geometry becomes less extreme. Yet even in these calmer regions, space-time is never truly empty. Energy exists in many forms, including vacuum energy, which contributes to the expansion of the universe. Space-time itself carries properties that influence cosmic behavior. Einstein's theory has passed every experimental test to date, from the bending of starlight during eclipses to the precise timing of pulsars and the detection of gravitational waves. It provides the framework for understanding how the universe's structure, from planets to galaxies to black holes, is governed by geometry rather than invisible forces acting across emptiness. At the same time, general relativity reveals its own limits. At singularities, equations break down, predictions become infinite and meaningless. This signals that a deeper theory is needed, one that can describe space-time at the smaller scales where quantum effects dominate. But even without that deeper theory, general relativity remains the foundation for understanding space, time, and gravity on all observable scales. Space-time is not a passive backdrop. It is an active participant in cosmic evolution. It stretches as the universe expands. It ripples when massive objects collide. It curves in response to matter and energy. It creates boundaries where escape becomes impossible, and horizons where information fades from reach. Galaxies move along paths shaped by this fabric. Light carries images of distant worlds along its curves. Black holes carve regions of no return into the structure of reality. The universe at every scale is defined not just by what exists within it, but by the geometry that binds everything together into a single, evolving whole. Dimensional space. The universe is not just something that exists in space and time. It is defined by how many directions exist at all. Every movement, every orbit, every wave of light depends on the number of dimensions available. Dimensions are not abstract ideas. They are the framework that determines what is possible. The universe we experience has 3 dimensions of space and 1 of time. Length, width, and height define where things are. Time defines when things happen. Together, they form a 4-dimensional structure, often described as 4D space-time. Every event in the universe has a position in space and a position in time. Nothing exists outside this structure as far as observation can tell. 3-dimensional space allows objects to have volume. It allows planets to orbit stars, stars to orbit galactic centers, and galaxies to move through clusters. If space had fewer dimensions, complex structures could not exist. In a 2-dimensional universe, stable orbits would be impossible. In a 1-dimensional universe, matter could not organize at all. 3 dimensions are the minimum required for a universe with long-lasting structure. Time adds a different kind of dimension. Unlike space, time cannot be freely navigated. Objects move through time in one direction only. This asymmetry is not built into geometry itself, but emerges from physical laws and cosmic evolution. Still, time is inseparable from space. Motion through space always involves motion through time, and changes in motion affect the flow of time itself. In 4-dimensional space-time, objects do not simply exist as shapes. They exist as paths. A planet is not a point moving through space. It is a continuous line through space-time, tracing an orbit that exists all at once as a geometric structure. The same is true for stars, galaxies, and even particles. Reality is not a sequence of static moments, but a connected 4-dimensional structure. This understanding immediately raises a question. If the universe has 3 spatial dimensions and 1 time dimension, could there be more? Physics does not forbid extra dimensions. In fact, several advanced theories suggest that additional spatial dimensions may exist, hidden from direct observation. The idea of extra dimensions did not emerge from imagination alone. It arose from attempts to unify the fundamental forces of nature. When physicists tried to combine gravity with quantum mechanics and other forces, the mathematics often required more dimensions than the 4 we experience. These extra dimensions are not added arbitrarily. They appear as natural consequences of the equations. One of the earliest ideas came from attempts to unify gravity and electromagnetism. By adding a 5th dimension to space-time, equations describing gravity could also produce electromagnetic behavior. In this view, electromagnetism emerged as a geometric effect of an additional spatial dimension. Although this specific model was incomplete, it introduced a powerful idea. Forces might be manifestations of geometry in higher dimensions. Modern theories take this idea much further. String theory, for example, proposes that the fundamental components of reality are not point-like particles, but tiny, vibrating strings. These strings can only exist consistently if space has more than 3 dimensions. Most versions of the theory require 10 or 11 total dimensions, including time. In these models, the extra dimensions are not extended like the familiar 3. They are thought to be extremely small, compact, and tightly curled, existing at scales far smaller than atoms. Every point in ordinary space would contain these additional dimensions, folded into complex shapes. Objects moving through space would also move through these dimensions, but the effects would be too subtle to detect directly with current technology. Another approach comes from brain world models, where the universe we experience is a 3-dimensional surface embedded in a higher dimensional space. In this view, ordinary matter and forces are confined to this surface, while gravity can extend into additional dimensions. This could explain why gravity is so much weaker than other forces. It is not weak because it is small, but because it spreads out into more dimensions than the others. These ideas are not speculative storytelling. They are mathematically precise frameworks developed to solve real problems in physics. They aim to reconcile general relativity, which describes gravity and space-time, with quantum mechanics, which governs particles and forces at the smaller scales. Extra dimensions offer possible solutions to inconsistencies that arise when these theories are combined. If extra dimensions exist, they would reshape the meaning of boundaries in the universe. In a purely 4-dimensional universe, boundaries arise from horizons, singularities, and limits imposed by light speed and expansion. In a higher dimensional universe, boundaries could be far more complex. A black hole, for example, is defined in 4 dimensions by an event horizon. This horizon marks the boundary beyond which information cannot escape. In higher dimensional space, black holes could have different shapes, sizes, and behaviors. Their horizons might extend or warp into extra dimensions, altering how they interact with the rest of the universe. Cosmic expansion itself could behave differently in higher dimensions. The expansion we observe might be confined to a 3-dimensional surface, while other dimensions remain static or evolve in different ways. The apparent edge of the observable universe might not correspond to any boundary in higher dimensional space, but only to limits within our dimensional slice. Extra dimensions could also define hidden boundaries that separate different regions of reality. Some models suggest that multiple 3-dimensional universes could exist within a higher dimensional space, each separated by small distances in extra dimensions. These regions would be invisible to each other except through gravity or rare, high-energy interactions. In such scenarios, the universe we observe would not be the entirety of existence, but a localized region within a larger dimensional structure. Boundaries would not be edges in space, but separations in dimensions we cannot access directly. 2 regions could occupy the same 3-dimensional location while being separated in an extra dimension, never interacting except through indirect effects. These ideas also affect how the beginning of the universe is understood. The Big Bang might not have occurred everywhere in higher dimensional space. It could have been an event localized to a lower dimensional region. Expansion could represent the stretching of a brain within a higher dimensional environment, rather than the expansion of all dimensions equally. Dimensional structure also influences how particles behave. The properties of particles, such as mass and charge, could be determined by how they move through extra dimensions. Vibrations or positions in these dimensions could define what kind of particle exists in ordinary space. This would mean that the diversity of matter is a geometric effect of higher dimensional motion. The concept of dimensional boundaries becomes especially important when considering the limits of observation. Instruments detect signals that propagate through our 3 dimensions of space and 1 of time. If other dimensions exist but do not allow electromagnetic signals to travel through them, they would remain hidden. Their presence would only be inferred through indirect gravitational effects or deviations from expected behavior. This introduces the idea that some boundaries are not visible because they do not block matter or light. They block interaction. A boundary in an extra dimension would not appear as a wall or horizon. It would appear as an absence of influence. Regions separated by such boundaries would evolve independently, unaware of each other's existence. Even within 4 dimensions, boundaries are defined by geometry rather than material barriers. The event horizon of a black hole is not a surface in space. It is a region where the structure of space-time changes so that escape becomes impossible. In higher dimensions, similar geometric boundaries could exist without obvious signatures. Time itself may behave differently across dimensions. Some theories allow for additional time-like dimensions, though these introduce severe physical challenges. Even without extra time dimensions, the flow of time in our universe could be influenced by the geometry of higher dimensional space. The arrow of time, defined by increasing entropy, might be tied to how dimensions unfold or interact. Dimensionality also determines what kinds of waves and fields can exist. Electromagnetic waves require 3 dimensions to propagate the way they do. Gravitational waves might propagate through additional dimensions, losing energy in ways that affect their observed strength. This possibility is actively studied through precise measurements of gravitational wave signals. The cosmic horizon that defines the observable universe could also be understood as a dimensional effect. In higher dimensional space, what appears as a horizon in 4 dimensions might be a projection of a more complex structure. The surface of last observation might not mark the limit of existence, but the limit of how our dimensional slice intersects with the rest of reality. Even if extra dimensions exist, they may be permanently inaccessible. Energy levels required to probe them could be far beyond what any experiment can reach. Their influence would be subtle, encoded in constants of nature and the behavior of gravity at extreme scales. This does not make them unscientific. It defines the challenge of detecting them. Dimensional space is not an optional feature of the universe. It is the foundation on which all physical laws operate. The number of dimensions determines how forces behave, how structures form, and how boundaries emerge. A universe with different dimensionality would not be a variation of ours. It would be fundamentally different in every measurable way. As physics pushes deeper into the structure of reality, dimensions become more than coordinates. They become active participants in cosmic evolution. They define what can interact, what can remain hidden, and where boundaries appear without surfaces or walls. The universe we observe may be a 4-dimensional cross-section of a larger dimensional structure. The limits we encounter may not be edges of existence, but edges of access. Dimensional space shapes not only where things are, but what kinds of things can be, how they connect, and where the universe appears to end, even when it does not. Time, entropy, and the second law. You see, time is not measured by clocks alone. In the universe, time reveals itself through change, through processes that move in one direction, and never reverse on their own. Stars ignite and burn their fuel. Galaxies form, collide, and slowly settle. Heat spreads, structures decay, and energy moves from concentrated states to more spread out ones. This directionality is not a coincidence. It is governed by one of the most fundamental principles in all of physics, the second law of thermodynamics. The second law states that in an isolated system, entropy always increases. Entropy is often described as disorder, but that description is incomplete. Entropy is more precisely a measure of how spread out energy and matter are, and how many possible microscopic arrangements exist for a system. A system with low entropy has energy concentrated in specific forms and locations. A system with high entropy has energy dispersed, diluted, and evenly distributed. The universe is the largest isolated system we know. Nothing lies outside it to exchange energy with. Because of this, the second law applies to the universe as a whole. From the earliest moments after the Big Bang to the far future, the total entropy of the universe has been increasing. And it will continue to increase as long as physical processes continue. The early universe had very low entropy, despite being extremely hot and dense. This may seem counterintuitive, but the key lies in gravity. Matter was distributed almost perfectly evenly. There were no stars, no galaxies, no black holes, no complex structures. Energy was concentrated, but it was arranged in a highly ordered way. This low entropy state set the direction of time. From that point forward, the universe could only evolve toward higher entropy. As the universe expanded, it cooled. Cooling did not reduce entropy. It allowed energy to spread into new forms. Gravity amplified tiny differences in density, causing matter to clump. This clumping increased entropy because it allowed more complex arrangements of matter and energy. Stars formed, burned fuel, and released radiation. That radiation spread into space, increasing entropy further. Every physical process that occurs increases total entropy. Nuclear fusion in stars converts mass into energy, releasing heat and light that disperse into surrounding space. Chemical reactions move toward lower energy states. Mechanical motion converts into heat through friction. Even the simple act of light traveling through expanding space increases entropy as wavelengths stretch and energy becomes more diluted. This irreversible increase defines the arrow of time. Physical laws at the microscopic level are mostly time-symmetric. Particles can interact in ways that look the same forward or backward in time. Entropy breaks this symmetry. Processes that increase entropy happen naturally. Processes that decrease entropy require precise conditions and external input. This is why shattered glass does not reassemble itself, and why heat does not spontaneously flow from cold regions to hot ones. On cosmic scales, entropy governs the life cycle of stars, galaxies, and the universe itself. Stars begin as dense clouds of gas, ignite, burn, and eventually exhaust their fuel. Massive stars collapse into neutron stars or black holes. Smaller stars cool into white dwarfs. These remnants represent higher entropy states than the stars that formed them. Black holes are especially important in discussions of cosmic entropy. They are not only objects of extreme gravity, but also the most entropic objects in the universe. A black hole's entropy is proportional to the area of its event horizon. As black holes grow by absorbing matter and merging with others, entropy increases dramatically. This means that the formation of black holes is one of the most efficient ways the universe increases its entropy. Galaxies themselves age through entropy-driven processes. Gas clouds are gradually converted into stars. Over time, available gas is depleted. Star formation slows. Galaxies transition from active, bright systems to quieter, older ones dominated by long-lived stars and stellar remnants. This gradual shift is part of what can be called cosmic aging. Cosmic aging does not refer to time passing on a clock. It refers to the loss of available energy to do work. Early in the universe, energy gradients were strong. Hot stars stood out sharply against cold space. Over time, these gradients weaken. Energy spreads out. Differences smooth over. The universe becomes more uniform, not in matter distribution, but in usable energy. Entropy also affects the expansion of the universe. As space expands, energy density decreases. Radiation stretches to longer wavelengths. Matter becomes more isolated. Structures become causally disconnected as distances grow faster than signals can travel. Expansion does not violate the second law. It accelerates entropy increase by giving energy more volume to spread into. The second law also explains why time has a beginning that matters. The universe did not have to start in a low entropy state. There are far more high entropy states than low entropy ones. The fact that the universe began in such an ordered condition is one of the deepest facts in cosmology. Everything that follows, including galaxies, stars, life, and observation itself, depends on this initial low entropy. As entropy increases, the universe moves towards states where fewer processes can occur. In the distant future, stars will no longer form. Existing stars will burn out. Black holes will dominate, then slowly evaporate through quantum effects over immense timescales. Energy will become thinly spread across vast space, approaching thermal equilibrium. This future state is often called heat death, not because the universe becomes hot, but because it becomes unable to sustain change. Temperature differences disappear. Energy is evenly distributed. No engines can run. No structure can grow. Entropy reaches its maximum possible value. The concept of an edge of the universe is deeply tied to entropy. The observable universe has boundaries defined by light and expansion. But entropy introduces another kind of boundary, a boundary of usable complexity. Regions beyond our observable horizon are not different in physical laws, but they are inaccessible. No exchange of energy or information can occur across that boundary. As expansion accelerates, more regions cross beyond causal contact. From our perspective, they fade beyond the cosmic horizon. Entropy still increases there, but independently. The universe fragments into isolated regions, each aging thermodynamically on its own. The edge is not a wall in space, but a limit in interaction. Entropy also defines the past horizon. The cosmic microwave background marks a time when the universe transitioned from opaque to transparent. Before that, information about earlier states is largely erased or smoothed out. High-energy interactions in the early universe erase details, leaving only statistical traces. Entropy increase hides the past as much as expansion hides the distant universe. Time, as experienced, is inseparable from entropy. Without entropy increase, time would have no preferred direction. Events could be reversed without contradiction. The universe would not have a history. The flow from low entropy to high entropy creates a narrative structure in the cosmos, where past, present, and future are physically distinct. On the larger scales, entropy provides a clock that does not tick in seconds, but in transformations. The formation of structure marks early times. The dominance of stellar remnants marks later times. The dominance of black holes marks even later epochs. Each stage represents a higher entropy configuration than the last. The edge of the universe, when viewed through entropy, is not just a spatial limit. It is also a temporal and thermodynamic limit. There are regions we cannot see because light cannot reach us. There are states the universe cannot return to because entropy has increased beyond them. The universe cannot rewind to its low entropy beginning. Every photon traveling through space, every star burning fuel, every black hole growing larger contributes to this irreversible progression. The second law is not a rule imposed from outside. It is a statistical consequence of how many ways matter and energy can be arranged. The universe follows it because there are overwhelmingly more ways to be disordered than ordered. Time moves forward because entropy increases. The universe evolves because it began in a state that allowed it to do so. The boundaries we encounter, whether horizons in space or limits in the future, are shaped as much by thermodynamics as by geometry or expansion. Entropy does not merely describe what happens in the universe. It defines what can happen, what cannot happen again, and where the universe ultimately runs out of possibilities. The edge of the universe. Look up at the night sky, and what you are really seeing is not space as it is now, but space as it was. Every point of light is a message that has been traveling for years, centuries, or billions of years before reaching your eyes. The universe does not present itself all at once. It reveals itself through time-delayed signals, and that delay is the key to understanding what scientists mean when they talk about the edge of the universe. The first and most important distinction is this: the edge of the universe is not automatically a physical boundary. It is not a cliff, a wall, or a place where matter suddenly stops. In modern cosmology, the word edge refers to a limit of observation, not a limit of existence. The universe may be far larger than what we can ever see, or it may even be infinite. But our access to it is restricted by the speed of light and the finite age of the cosmos. This is where the idea of the observable universe comes in. The observable universe is the region of space from which light has had enough time to reach us since the Big Bang. Because the universe is about 13.8 billion years old and light travels at a fixed speed, there is a maximum distance from which information can arrive. That distance defines a spherical boundary centered on Earth, not because Earth is special, but because observation is always centered on the observer. This observable boundary is often mistaken for an edge in the everyday sense. In reality, it is more like a horizon. Just as the ocean appears to end at the horizon even though it clearly does not, the universe appears to end where light has not yet reached us. Beyond that horizon, galaxies may exist, structures may form, and physical laws may still operate, but they are causally disconnected from us for now. The concept becomes even more subtle when cosmic expansion is taken into account. The universe is not static. Space itself is stretching, carrying galaxies away from one another. This means that the most distant objects we can see today were once much closer when their light began its journey. The observable edge is not a simple distance measured with a ruler. It is a moving boundary shaped by time, expansion, and the history of the universe itself. The idea of a true edge, a final boundary where reality ends, has no confirmed basis in current physics. General relativity allows space to be finite without having an edge, much like the surface of a sphere. You can travel indefinitely on a sphere without ever encountering a boundary, yet the surface area is finite. In 3 dimensions, a similar geometry could apply to space itself, curved in ways that do not require an ending wall. This distinction matters because it reframes the question entirely. Instead of asking, what is at the edge, physicists ask, what limits what we can observe? That shift moves the discussion from speculation to measurable science, grounded in light, time, and geometry. Observable horizon versus true edge. The observable horizon is defined by physics, not imagination. It exists because the universe has a beginning and because signals cannot travel faster than light. The cosmic horizon marks the maximum distance from which any causal influence can reach us. Everything beyond it is, for now, invisible and unreachable. The radius of the observable universe is about 46 billion light-years, even though the universe is only 13.8 billion years old. This seeming contradiction arises because space has been expanding while light was traveling through it. As photons move toward us, the space between us and their source stretched, increasing the final distance. The observable universe is therefore much larger than the naive calculation of age multiplied by light speed. This horizon is not fixed. As time passes, more light from distant regions reaches us, and the observable universe grows. However, there is a competing effect. Because the expansion of the universe is accelerating due to dark energy, some regions are moving away from us so fast that their light will never reach us, no matter how long we wait. This creates a cosmic event horizon, a future boundary beyond which events are permanently unobservable. The true edge, if it exists at all, would lie beyond all horizons. It would be a property of the global structure of space, not something defined by observation. Current measurements of cosmic curvature suggest that the universe is very close to flat. A flat universe can be infinite, extending endlessly in all directions, or it can be finite with complex topology. Observation so far cannot distinguish between these possibilities. Importantly, no experiment has ever detected a boundary where physical laws break down simply because space ends. The laws of physics appear uniform across the observable universe. Galaxies at the edge behave according to the same principles as galaxies nearby. Radiation follows the same rules. Matter obeys the same conservation laws. This uniformity strongly suggests that the universe does not suddenly change character at the observable limit. Light is the ultimate speed limit of the universe, and it shapes every cosmological boundary we know. When astronomers observe distant galaxies, they are effectively looking back in time. A galaxy observed at a distance of 10 billion light-years is seen as it was 10 billion years ago, long before Earth existed. As we approach the cosmic horizon, we approach the earliest moments of structure formation. Beyond a certain distance, galaxies do not exist yet. Matter had not collapsed into stars. Space was filled with hot plasma. Push farther still, and even atoms could not survive. The cosmic horizon therefore corresponds not just to distance, but to a sequence of physical eras. The cosmic microwave background marks a critical boundary in this sense. It is the oldest light we can observe, released when the universe cooled enough for electrons and protons to combine into neutral atoms. Before this moment, the universe was opaque to light. Photons scattered constantly, unable to travel freely. The CMB forms a spherical shell around us, representing the surface beyond which we cannot see using electromagnetic radiation. This surface is sometimes called the surface of last scattering, and it functions like a visual wall, not because nothing exists beyond it, but because light from earlier times cannot reach us. Beyond this surface lies a universe that can only be studied indirectly, through gravitational waves, neutrinos, or theoretical models. The cosmic horizon is therefore layered. First comes the limit of visible galaxies, then the CMB. Beyond that lies the realm of inflation, quantum fluctuations, and energies far beyond anything we can reproduce in laboratories. Each layer represents a deeper boundary, not of space, but of accessible information. The idea of a literal wall, a place where space ends and nothing lies beyond, is a powerful image, but it does not fit comfortably within established physics. General relativity does not require space to have an edge, and quantum field theory assumes fields exist everywhere in space-time, not just within a bounded region. A wall of nothing would imply a preferred direction or location in the universe, violating the principle of isotropy, which states that the universe looks the same in all directions on large scales. Observations strongly support this principle. The CMB is nearly uniform in every direction, with tiny fluctuations that match predictions from inflationary theory. There is no sign of an abrupt asymmetry that would hint at a nearby boundary. Even speculative models that involve higher dimensions or brane cosmology do not typically place a hard edge within our observable universe. Instead, They suggest that our universe may be embedded within a higher dimensional structure, where boundaries exist in dimensions we do not directly perceive, not as walls in ordinary space. If a literal edge existed and were close enough to observe, it would likely leave detectable signatures. Light would behave differently near it. Matter distributions would show distortions. Gravitational effects would betray its presence. So far, no such signatures have been found. The absence of evidence does not prove non-existence, but it does place strong constraints on what an edge could be. In modern cosmology, the edge is not a place you could travel to. It is a limit defined by time, expansion, and causality. What ultimately defines the edge of the universe is not emptiness, but information. Beyond the observable horizon, events cannot affect us, and we cannot affect them. They are causally disconnected. This causal structure is central to how physicists understand reality on the larger scales. Black holes provide a useful analogy. A black hole has an event horizon, not a solid surface, but a boundary beyond which information cannot escape. To an outside observer, the horizon behaves like an edge, even though space-time continues inside. The universe as a whole may have similar horizons, defining regions of accessibility rather than existence. In this sense, the edge of the universe is not a failure of space, but a feature of space-time itself. It arises naturally from the interplay between the speed of light, the expansion of space, and the finite age of the cosmos. It is not a defect or a mystery waiting to be patched with speculation. It is a measurable, predictable consequence of well-tested physical laws. As telescopes improve and new messengers like gravitational waves are detected, the practical edge of observation may shift. We may see farther, earlier, and deeper into cosmic history. But no matter how advanced our instruments become, some boundary will always remain, defined not by technology, but by the structure of space-time itself. The universe does not end where our vision ends. It simply continues beyond our reach, unfolding according to the same rules, indifferent to whether it is observed or not. Life on the boundary. At the outermost reaches of space, the universe begins to resemble a place completely alien to human experience. It is not merely emptiness, it is a landscape defined by extremes. Gravity may be nearly absent, yet punctuated by distant, massive objects whose pull stretches across unimaginable distances. Radiation from collapsed stars and the cosmic microwave background still permeate space, but at levels far weaker than near galaxies. In these regions, the laws of physics operate exactly the same way as they do here, but the conditions are so hostile that ordinary matter behaves differently. Energy is sparse, and the rules that sustain life on a planet like Earth cannot exist in the same form. Speculative physics allows us to imagine what forms of life, if any, could survive under these conditions. Life as we know it depends on energy flows, chemical gradients, and a local environment capable of sustaining complex molecules. At the boundary, energy sources are minimal. Stars are so distant that photons arrive infrequently. Cosmic rays travel unimpeded, striking atoms with destructive force. Yet in the gaps between galaxies and clusters, subtle processes may provide rare niches where energy is concentrated enough to support highly unusual systems. Perhaps life here would not be based on carbon chemistry at all. Perhaps it would be a network of fields or fluctuations in exotic matter, self-organizing in ways impossible to see directly. Radiation plays a dual role in these extremes. On one hand, it is lethal, fragmenting molecules and disrupting delicate processes. On the other, it is a carrier of energy, the only source for any system seeking to do work at the edge. Life, if it exists, would have to exploit this radiation efficiently, converting sparse photons or cosmic particles into usable energy. Conventional life that relies on heat, liquid water, or sunlight could not survive. These regions demand mechanisms of survival entirely alien to terrestrial experience, relying on energy storage, resilience to particle bombardment, or even harnessing vacuum fluctuations in quantum fields. Gravity at the edge behaves differently than we experience locally. Galaxies pull gently at one another across voids, but the force is diffuse. In principle, this allows loosely bound structures to drift across space for billions of years without colliding. This slow, extended motion would shape any hypothetical life forms or processes that exist here. Organisms, or whatever forms of persistence exist, might spread over enormous volumes, moving imperceptibly for eons. Time, warped slightly by weak gravitational curvature, could give rise to lifetimes measured in billions of years, and evolution could operate over timescales utterly inconceivable in terrestrial terms. Isolation dominates these regions. Causally disconnected from much of the universe, systems at the outer boundaries are effectively alone. Communication is impossible across cosmic horizons, and resources are dispersed. This isolation would favor forms of life or self-organizing structures that do not rely on interaction. Instead of ecosystems, there could be solitary processes, self-contained energy cycles, or extremely slow reactions preserved by near absolute vacuum and minimal thermal agitation. Survival here is measured not in minutes or years, but in how well a system persists against entropy in near-perfect isolation. This is where the concept of the surface of oblivion arises. Beyond the observable universe, space is a region beyond any visible light, beyond causal contact, and beyond current observation. The surface is defined not by a tangible wall, but by the point at which photons from early times have not yet, or will never, reach us. It is a horizon of invisibility, an unobservable realm where matter and energy continue to exist, but no signal from them can ever arrive. From our perspective, this is a literal edge of knowledge. Anything crossing this boundary slips beyond the reach of observation, slipping into effective cosmic oblivion. The cosmic microwave background, CMB, marks the last visible signal from the early universe. It is the afterglow of recombination, when the universe cooled enough for photons to travel freely, forming the oldest light detectable today. Beyond this surface, photons had not yet decoupled from matter. Regions farther out remain opaque in electromagnetic terms, yet they exist in reality, carrying structures, energy, and events that could never be observed directly. The CMB functions as a visual boundary, separating the known universe from the unknowable stretches beyond. Temperature at these extreme edges approaches absolute zero, the coldest limit allowed by physics. Gas densities drop to minuscule values, radiation is redshifted into near invisibility, and matter floats in a near-perfect vacuum. Under such conditions, kinetic energy is nearly absent. Atoms move sluggishly, interactions become rare, and the possibility for conventional chemistry vanishes. Any life attempting to exist here would need to survive on processes that are fundamentally quantum mechanical, possibly relying on fluctuations in vacuum energy or subtle gradients that persist despite the extreme conditions. The vacuum itself becomes a defining factor. Space is not a simple void. It is a quantum field teeming with ephemeral particles that flicker into and out of existence. These fluctuations, though faint, represent the only continuous energy in the void. Life at the boundary could, in principle, tap into these fluctuations, using them as a minimal source of energy or information. The scarcity of interaction with other matter and radiation would turn every fluctuation into a valuable event, a resource to maintain structure against the relentless drive of entropy. Cosmic isolation, near absolute cold, and extreme vacuum combine to produce an environment of profound stillness. Time stretches differently here as well. Expansion increases distances exponentially, stretching wavelengths of radiation and making interactions progressively rarer. Matter drifts apart into near-infinite voids, so the concept of a localized environment takes on new meaning. A system existing in one of these regions might experience effective permanence, but at the cost of extreme scarcity, exposure, and isolation. The surface of oblivion is more than an abstract idea. It is a practical boundary of energy, interaction, and information. Beyond the reach of light, matter and energy may continue to evolve according to local laws, but no observer within our causal patch can ever witness it. The combination of near-zero temperature, low radiation density, and near-total isolation produces a cosmic landscape unlike any familiar environment, a place where the rules of life and structure would have to stretch to the very limits allowed by physics. At the same time, these extreme conditions are the ultimate test of survival against the second law of thermodynamics. Entropy relentlessly increases everywhere, even in the farthest reaches. Sparse energy sources and weak radiation impose limits on the complexity of any process. Life, or any self-organizing system, must operate within these constraints, adapting to isolation, scarcity, and extreme vacuum. Persistence becomes the primary measure of survival, and energy efficiency becomes absolute. Radiation, gravity, and vacuum combine into a cosmic architecture that defines boundaries not as walls or edges, but as gradients of possibility. The farther one moves from luminous matter, the less structure is imposed by stars and galaxies. The colder the environment, the slower the passage of usable energy, and the closer one comes to the ultimate isolation of the universe's horizon. Here at the edge, survival is defined not by competition, but by resilience to time and entropy, measured over scales of billions of years. The extreme edges of the cosmos offer a glimpse into physics in its purest form. They are laboratories for fundamental processes, revealing the behavior of matter, energy, and radiation in the absence of conventional support structures. Any hypothetical life here would not resemble terrestrial biology. It would operate in the slow, diffuse medium of near-perfect vacuum, constrained by entropy, dependent on rare radiation events and shaped by gravitational subtleties. These systems could persist for eons, invisible to the rest of the universe, existing in near-total isolation, yet fully subject to the laws that govern all of space-time. The surface of oblivion, defined by the last photons reaching us from the early universe, is also a temporal boundary. It represents the farthest point in time we can observe directly. Beyond it lies a region where matter and energy may exist, but whose history is inaccessible. Expansion ensures that many such regions will remain permanently beyond reach, drifting away faster than light can traverse the intervening space. Here, the observable and the real diverge. Physics operates, but observation does not. Temperature, vacuum, isolation, and radiation combine to produce the ultimate frontier. It is a space not of emptiness, but of extreme conditions, where physics reigns in stark clarity, and life, if it exists, must find entirely new modes of persistence. These boundaries define the limits of observation, the challenges of survival, and the extreme edge of all that we can hope to know. The boundary is not a wall. It is a gradient, a shift from structured energy to diffuse emptiness. It is the final stage of cosmic environment where structure thins, interactions slow, and conditions approach the theoretical extremes allowed by nature. Radiation, gravity, vacuum, and entropy converge to produce a landscape that is stark, silent, and absolute. Life, survival, and persistence here would be determined not by abundance, but by endurance. Every fluctuation, every photon, every particle becomes precious, and every process is stretched to the limit by time and isolation. The surface of oblivion and the extreme edges beyond observable light are the ultimate laboratory for physics, cosmology, and speculative life. They are defined not by the presence of matter, but by the absence of access. Here, the universe demonstrates its vastness, its extremes, and the remarkable precision with which its laws operate, even where nothing seems to exist. Fundamental forces and laws. Electromagnetism is the force that makes the universe visible. It governs light, the very photons that carry information across billions of years to reach our eyes, our telescopes, and our instruments. Every color, every glimmer of a distant star, every structure revealed by radiation depends entirely on the behavior of electromagnetic waves. From radio waves to gamma rays, this force dictates not only what we can observe, but how the universe itself organizes on scales both small and vast. Without electromagnetism, the universe would be a silent, dark expanse, devoid of the light and energy gradients that allow structure, measurement, and life to exist. Photons, the particles of light, are the carriers of electromagnetic forces. They travel at the ultimate cosmic speed limit, forming a bridge between objects separated by incomprehensible distances. Every time we observe a galaxy millions or billions of light years away, we are seeing photons that embarked on their journey long before Earth existed, long before the solar system coalesced. Electromagnetic waves provide the universe with its observable history. They are the only messengers capable of delivering data from the farthest reaches of the cosmos, yet even they have limits, boundaries dictated by physics. The first limit comes from distance and expansion. As space stretches, photons are redshifted, their wavelengths lengthening until they reach energies far too low to interact detectably with matter. Light that left a galaxy billions of years ago may arrive as microwave radiation or radio waves, signals so faint that extraordinary instruments are required to detect them. Beyond certain distances, even the most sensitive telescopes cannot observe light because it has been stretched beyond detectable thresholds. The cosmic horizon, therefore, is defined in part by the properties of electromagnetic waves and their finite energy, which limits observation of the farthest structures. The second limit arises from absorption and scattering. Light cannot travel unimpeded through all regions of space. Dense gas clouds, dust, and plasma absorb or scatter photons, preventing them from reaching observers on Earth. This creates natural boundaries within the observable universe. Regions behind thick molecular clouds or deep within star-forming galaxies can remain invisible even when relatively nearby in cosmic terms. Electromagnetism, which allows us to see it all, simultaneously imposes constraints on how far and what we can perceive. Electromagnetic waves also define the spectrum of visibility. Human eyes can only detect a narrow slice of the electromagnetic spectrum, from red to violet. The majority of cosmic signals exist in wavelengths far beyond this: infrared, ultraviolet, X-rays, gamma rays, and radio waves. Specialized instruments extend observation into these regimes, revealing phenomena invisible to human perception. Jets from black holes, interstellar gas dynamics, cosmic microwave background radiation, and the faint glow of the first stars. Without electromagnetism, none of this information could propagate. Without understanding its behavior, we could not translate these signals into images or data. Even the most powerful light can be blocked by cosmic distance. Photons travel, but only through space-time that allows interaction. Beyond the cosmic microwave background, the universe was opaque to light. Before photons decoupled from matter, energy was trapped, scattering endlessly in the primordial plasma. Electromagnetic waves did not convey information beyond that point. The first visible signals arrive only after recombination, roughly 380,000 years after the Big Bang, establishing a practical limit to electromagnetic observation. What lies before remains hidden, detectable only indirectly through gravitational effects or particle messengers like neutrinos. Electromagnetism is intimately connected to the structure of matter. Atoms form because electrons are bound to nuclei through electromagnetic forces. Molecules emerge through the sharing and exchange of electrons. Planets, clouds, and interstellar dust owe their stability to these forces. In essence, the fabric of the visible universe, the very material that emits light, exists because of electromagnetic interaction. Without it, there would be no stars to illuminate the cosmos, no galaxies to structure space, and no radiation to carry their image across time. The speed of light, set by the electromagnetic constants of the vacuum, defines the ultimate speed limit for the universe. Information cannot travel faster. This enforces causality, creating a rigid structure of what can be observed and when. Events beyond a certain distance are permanently unreachable, not because matter ceases to exist, but because electromagnetic signals cannot traverse the space-time gap fast enough. The edge of the observable universe, the cosmic horizon, is defined by this limitation. Every photon carries not only information, but also the boundary of knowledge, establishing where observation ends, even as reality continues. Electromagnetism interacts with other fundamental forces, but remains uniquely critical for observation. Gravity shapes galaxies and the motion of matter. The strong nuclear force binds atomic nuclei, and the weak nuclear force governs certain particle decays. Yet only electromagnetism generates detectable radiation across vast distances, turning matter into information. Without it, the cosmos would be a dark, inscrutable void, invisible across light years. Every image of a nebula, every spectral line, every map of cosmic structure is a consequence of electromagnetic interaction. Even in extreme environments near black holes or at the edges of expanding voids, electromagnetic waves define limits. Gravitational lensing bends light, but photons still travel along paths dictated by both space-time curvature and electromagnetic propagation. Redshift stretches wavelengths, dimming intensity. Regions beyond certain distances or densities become effectively invisible, not because light fails, but because physical conditions render electromagnetic signals inaccessible. Radiation itself carries energy, a second layer of constraint. High-energy photons, like gamma rays, can alter matter, ionize atoms, and destroy fragile structures. Low-energy photons stretched by expansion may carry little usable energy, limiting the capacity to detect or interact. Electromagnetism, therefore, is both the messenger and the regulator, defining what we can see while setting strict natural limits on observation. The cosmic microwave background exemplifies this dual role. It is the oldest electromagnetic signal accessible to us, revealing the structure of the early universe. Beyond it, photons cannot escape. Interactions in the primordial plasma erase information, and light fails to provide a window. Electromagnetic radiation sets the ultimate observational boundary. This surface of last light is the edge of knowledge in visible terms. Reality continues beyond it, but photons will never deliver that information. Conservation of energy. The universe is a theatre of motion, an endless symphony of energy shifting from one form to another, from star to star, galaxy to galaxy, from the heart of a black hole to the vast emptiness between. Every explosion, collision, and flicker of light is a transaction in this cosmic ledger, governed by one of the most fundamental principles in physics, the conservation of energy. Energy can neither be created nor destroyed, only transformed. It is the thread that weaves together the complex tapestry of the cosmos, determining the behavior of matter, the evolution of galaxies, and the ultimate fate of the universe itself. At the smaller scales, energy manifests in particles, vibrations, and electromagnetic fields. In atoms, electrons orbit nuclei because they carry kinetic energy balanced with potential energy, forming stable configurations that make matter possible. At larger scales, energy powers the fusion in stellar cores, drives the expansion of space, and fuels the jets of black holes. On cosmic scales, conservation of energy constrains the motion of galaxies and the dynamics of clusters. It shapes the cosmic web, governs interactions across unimaginable distances, and defines the limits of what can happen at the outermost reaches of the universe. The principle itself is deceptively simple. No matter how chaotic a system appears, the total energy remains constant. When a star explodes as a supernova, mass is converted into kinetic energy, heat, and light. When a black hole swallows matter, energy is redistributed, encoded in gravity, radiation, or rotational motion. The universe operates as a giant, self-regulating accounting system. Every photon that traverses billions of light years, every particle that drifts through near-empty voids, is part of this ongoing balance, a signal that energy continues to flow, even at scales we cannot directly observe. As we move toward the edge of the observable universe, the rules of energy take on extraordinary significance. Distance, expansion, and time all interact with energy to define what is possible. Light from distant galaxies is stretched by cosmic expansion. Its wavelength elongated, its energy diminished. This redshifting reduces the capacity of photons to interact with matter, a limit imposed not by destruction, but by the distribution of energy across expanding space. Energy is not lost, it is conserved, but it becomes less concentrated, less capable of driving processes in the extreme outskirts of the cosmos. At these edges, matter itself behaves differently. Gas densities are incredibly low, radiation is diffuse, and gravitational influence is weak. Kinetic energy, once abundant in galaxies and clusters, is almost entirely dissipated across near infinite volumes. Particles drift slowly, occasionally interacting, but mostly isolated. Energy exists, but its scarcity creates an environment where traditional structures and processes cannot persist. Stars cannot ignite, chemistry cannot operate as on planets, and the usual engines of life and activity are absent. The universe's edge is a realm where energy is present but spread thin, defining a boundary not of space, but of practical interaction. This brings us to absolute zero, the ultimate temperature limit of the cosmos. Absolute zero is not merely cold, it is the point at which all classical motion of particles ceases. In the vast emptiness between galaxies, temperatures approach this limit. Cosmic background radiation provides a faint residual energy, only 2.7 Kelvin above absolute zero, a whisper of heat remaining from the Big Bang. Matter at these extremes exists in near-perfect vacuum conditions, kinetic energy almost vanishing, chemical interaction stalled, and entropy gradually dominating all processes. Temperature and energy are intimately connected. Even at the edge, quantum effects persist. Particles exhibit zero-point motion, tiny fluctuations that cannot be eliminated even at absolute zero. These quantum effects prevent matter from freezing completely in the classical sense, creating a subtle energy background that pervades the emptiest regions of space. At these scales, energy is both conserved and minimized, providing a stable but almost inert framework in which the universe continues to exist. The interplay of conservation of energy and absolute zero shapes the limits of cosmic structure. Galaxies, clusters, and filaments exist because energy allows matter to collapse against gravity. At the edge, where energy density is vanishingly small, such structures cannot form. Matter is diffuse, collisions are rare, and gravitational clumping slows dramatically. Energy is present, conserved in every particle and photon, but it is insufficient to overcome the vast distances and near-zero temperatures that define these extreme regions. Even radiation obeys the rules of energy conservation at the edge. Photons traveling across billions of light-years carry energy, yet cosmic expansion reduces their frequency and intensity. Gamma rays emitted by distant quasars or X-rays from collapsing stars eventually lose energy through redshift, spreading their energy across ever larger volumes of space. The universe is not losing energy in this process, but the usable energy density decreases. Processes that rely on concentrated energy, fusion, chemical reactions, or the growth of complex structures become increasingly improbable. Energy at the cosmic edge is also influenced by dark energy. The accelerated expansion of space, driven by dark energy, does work on the universe by stretching space itself. This affects the energy of photons, the dynamics of matter, and the limits of causal interaction. While total energy is conserved, it becomes distributed over exponentially expanding volumes, rendering much of it effectively unavailable for conventional processes. The universe at the edge is a place of conservation and scarcity simultaneously, a realm where the law holds perfectly, yet the practical consequences are extreme. Matter near absolute zero behaves in unusual ways. Classical motion is nearly absent, but quantum behavior dominates. Particles exhibit wave-like properties, fields fluctuate gently, and long-range interactions, though weak, can persist over enormous distances. These conditions are harsh for life or complex chemistry, yet they represent a form of stability. Energy persists in a near equilibrium state, preserved across cosmic timescales. The edge of the universe is, in effect, a repository of preserved energy, but one so diffuse that traditional forms of structure are no longer viable. The conservation of energy also frames the concept of the ultimate cosmic horizon. Photons emitted from the farthest galaxies carry energy that will never interact with us again if they are beyond the event horizon created by accelerated expansion. The energy exists, it is conserved, but it is forever causally disconnected from our observable patch. The universe, in this sense, contains more energy than we can ever access, and that energy defines the boundaries of observation, interaction, and influence. In extreme isolation, the interplay of energy, temperature, and quantum effects defines the limits of possibility. Particles drift through cold voids, retaining kinetic and potential energy in near-perfect equilibrium. Radiation persists, but is faint. Quantum fluctuations provide minimal activity, yet all energy is accounted for. Nothing is lost. Everything exists in the form dictated by physical laws. Conservation is absolute, yet practical interaction is negligible. The universe at its edge is a place where energy continues to exist, undiminished in principle, but stretched and diluted across near infinite scales. Matter itself responds to these conditions in remarkable ways. Atomic motion slows, chemical reactions are suppressed, and gravitational interactions weaken. Structures that rely on concentrated energy cannot form. Stars, planets, and life, as known to us, are impossible. Energy persists, but it is spread thin, defining a boundary of possibility. These regions are almost frozen in time relative to dense, energy-rich environments. In this way, the edge of the universe is not defined by walls or limits of space, but by the diminishing capacity of energy to produce conventional effects. Temperature and energy are intertwined. Even in the coldest regions, residual photons from the cosmic microwave background maintain a minimal energy floor. Absolute zero cannot be reached entirely due to zero-point motion, quantum fluctuations that guarantee the persistence of subtle energy even in the emptiest voids. Energy is conserved, motion persists on a quantum scale, and matter exists in stable but extreme forms. The surface of absolute limits in the universe is therefore both energetic and thermodynamic. Energy persists across the cosmos, constrained by fundamental laws, yet limited in its practical ability to create, move, or sustain structures. Matter exists near absolute zero, effectively frozen in diffuse arrangements, interacting only rarely, and yet obeying the same laws that govern the most active stars and galaxies. At the boundary of the observable universe, conservation of energy and near absolute temperature define the environment. Radiation is weak, matter is sparse, and quantum fluctuations dominate. The universe continues to exist in these extreme conditions, but the forms and processes familiar to us cannot operate. The edge is a realm where energy is preserved, but its practical effects are minimal, where absolute zero establishes the baseline of cosmic possibility, and where the laws of physics maintain perfect order even in isolation. This combination of energy conservation and absolute temperature limits explains why the edge of the universe is a boundary of interaction, not of existence. Energy remains present everywhere, matter persists, and quantum fields continue to fluctuate. Yet the universe becomes almost inert at these extremes. Structures fail to form, interactions are rare, and any processes are incredibly slow. The physical laws are unchanged, but their manifestations become subtle, diffuse, and spread across scales that challenge imagination. At the universe's edge, we see the ultimate demonstration of two principles. Energy cannot be destroyed, and temperature cannot go below absolute zero. They set absolute limits, defining what is possible, what is improbable, and what is effectively frozen in the grand, expanding cosmos. Conservation of energy guarantees that nothing vanishes, while near zero temperature ensures that nothing functions in familiar ways. Together, they create a universe that is still alive with physics, even in regions far beyond our direct observation. A cosmos that is conserved, enduring, and defined by its fundamental laws at every scale, including the extreme reaches of space and time. Extreme cosmic phenomena. Black holes are the universe's ultimate enigmas, the points at which space, time, and gravity converge into extremes so profound that conventional understanding falters. These objects are not simply dense stars or collapsed remnants. They are regions where matter is compressed beyond imagination. Gravity curves space to the point of no return, and the familiar rules of physics begin to bend. At the heart of every black hole lies a singularity, a theoretical point where density becomes infinite, where the curvature of space-time grows without bound, and where energy and matter are compressed into a scale that defies direct observation. Around this singularity exists a boundary known as the event horizon, a conceptual edge that defines the limit of the black hole's influence. The event horizon is perhaps the most famous and misunderstood feature of black holes. It is not a physical surface that you could touch or see. It is a mathematical boundary, an invisible sphere surrounding the singularity. Anything crossing this threshold, whether particle, light, or information, cannot escape the gravitational pull. From the outside, the event horizon functions as an edge within the cosmos, a boundary of causal influence. Beyond it, events unfold in isolation from the rest of the universe. The horizon is the ultimate demonstration of the principle that space itself can create an edge, not as a wall of matter, but as a limit imposed by gravity and the fabric of space-time. At the event horizon, familiar notions of time and space break down in extraordinary ways. For a distant observer, an object approaching the horizon appears to slow, its motion stretched until it seems frozen at the edge. Photons emitted by the object are redshifted to invisibility, losing energy as the curvature of space-time bends their path. From the perspective of the object itself, time continues normally, but its trajectory is irrevocably drawn inward, never to return. The event horizon thus represents a paradox of observation. It is both a boundary that isolates matter and a lens through which extreme gravitational effects can be studied. Hawking radiation introduces a second layer of complexity to black holes. In the 1970s, Stephen Hawking proposed that black holes are not entirely black, but emit radiation due to quantum effects near the event horizon. This radiation arises from virtual particle pairs that form and annihilate constantly in the vacuum of space. Occasionally, one particle falls into the black hole, while the other escapes, carrying energy away. This process causes the black hole to lose mass over time, a phenomenon that challenges the traditional notion of black holes as permanent, unchanging objects. The slow evaporation of black holes through Hawking radiation highlights a profound interplay between quantum mechanics, gravity, and thermodynamics. The information paradox emerges from this interplay. Classical physics predicts that anything falling into a black hole is lost forever, including the information encoded in its physical state. Quantum mechanics, however, asserts that information cannot be destroyed. The tension between these principles has led to one of the most significant debates in modern physics. Does information disappear into the singularity, or is it somehow preserved in the Hawking radiation? Recent theoretical advances suggest that information may be encoded on the event horizon itself, or possibly transmitted via subtle quantum correlations, a hypothesis that hints at a deep underlying connection between gravity, quantum mechanics, and the nature of reality. Black holes vary widely in scale and origin. Stellar mass black holes form from the collapse of massive stars, their gravitational pull strong enough to trap all nearby light. Supermassive black holes, millions or billions of times the mass of the Sun, occupy the centers of galaxies, orchestrating the motion of stars and gas across immense distances. Intermediate mass black holes, less common and more mysterious, may link the formation of stellar and supermassive varieties. Despite differences in size, all black holes share the same fundamental properties: a singularity at the center, an event horizon, and a profound effect on the surrounding space-time. The edges within edges concept becomes particularly vivid when considering black holes in the context of the universe. Each black hole is a localized edge, a point where normal space-time ceases to behave in familiar ways. These microcosmic boundaries reflect, in miniature, the broader cosmic boundaries explored elsewhere, the limits of observation, the horizons imposed by the speed of light, and the causal isolation that defines the edge of the universe. Black holes are the ultimate expression of boundaries within the cosmos, demonstrating that edges do not require walls, only curvature, and the laws of physics taken to their extremes. Gravity near a black hole exhibits phenomena that defy everyday intuition. Space is stretched, light paths bend, and time itself slows relative to distant observers. The intense warping of space-time produces tidal forces so strong that objects are stretched and compressed, a process known as spaghettification. Matter falling inward is torn into streams, its energy redistributed across the gravitational well. These processes occur within a framework dictated by Einstein's general relativity, yet they intersect with quantum mechanics in ways that remain incompletely understood. Each infalling particle carries energy, angular momentum, and information, all of which interact with the black hole's extreme gravitational field. Accretion disks surrounding black holes illustrate how energy behaves in these extreme regions. Gas, dust, and debris spiral inward at near-light speeds, heating to millions of degrees as gravitational potential energy converts into radiation. X-rays and gamma rays emitted from these disks provide some of the most direct observational evidence of black holes, even though the singularity and event horizon themselves remain invisible. In effect, energy at the edge of a black hole is both trapped and liberated, confined by gravity yet radiating outward through complex interactions. Black holes also influence cosmic structure on grand scales. Supermassive black holes regulate the formation of galaxies by controlling the flow of gas, triggering star formation or suppressing it through energetic outflows known as jets. These jets, often extending thousands of light years, demonstrate how extreme gravitational boundaries can shape energy distribution far beyond their immediate vicinity. The interplay of mass, gravity, and energy at these edges drives the evolution of the observable universe, linking local extremes to cosmic architecture. The singularity itself remains one of the greatest mysteries. It represents a point where densities approach infinity and current physical theories break down. Quantum gravity, string theory, and other approaches aim to describe what happens within this boundary, suggesting that space-time may have discrete structure at the smallest scales. The singularity embodies a limit, a place where conventional physics ceases, yet one where energy and information persist in forms not yet fully understood. It is the ultimate edge within the edge, where the universe's rules are pushed to the extreme. Observational advances continue to reveal more about black holes and their horizons. The Event Horizon Telescope captured the first image of a black hole's silhouette in the galaxy M87, directly visualizing the shadow cast by the event horizon. Gravitational wave observatories like LIGO and Virgo detect ripples in space-time from black hole mergers, offering insights into mass, spin, and energy distribution. These observations bridge theory and reality, confirming the existence of cosmic boundaries that were once purely mathematical constructs. Even at the edges of black holes, conservation laws hold. Energy, momentum, and angular momentum remain accounted for, whether in matter plunging inward or radiation escaping via Hawking processes. The universe preserves its balance, even in regions where intuition suggests chaos. The paradoxes and extremes encountered near black holes are not failures of physics. They are tests of the universal laws in their most severe conditions. Black holes also challenge the notion of isolation. Their gravitational influence extends far beyond the event horizon, warping space-time and affecting surrounding matter over thousands of light years. Jets, radiation, and gravitational waves carry energy and information outward, connecting these extreme edges to the broader universe. In this sense, black holes demonstrate that even at the most extreme boundaries, energy and causality remain active, linking local phenomena to cosmic-scale dynamics. Finally, black holes illuminate the concept of cosmic limits. The event horizon is a literal edge for observation, beyond which no signal returns. The singularity is a theoretical edge for matter, beyond which classical physics cannot penetrate. Hawking radiation and quantum effects hint at processes that bridge these extremes, suggesting that edges in the universe are not absolute, but defined by the interplay of energy, gravity, and information. Black holes, therefore, are both the ultimate cosmic edge and the key to understanding the nature of edges themselves, revealing how extreme physics shapes what can exist, what can be observed, and what remains forever beyond reach. Quantum mechanics. The universe, at its most fundamental level, is stranger than any telescope or theory can fully capture. Beneath the grand spirals of galaxies, beneath the glow of stars, beneath even the curvature of space-time dictated by gravity, there exists a layer of reality governed not by certainty, but by probabilities, vibrations, and invisible fluctuations. This is the domain of quantum mechanics, where the rules of the cosmos appear to twist, and the very concept of edge takes on a new, almost surreal meaning. At these scales, matter and energy are not continuous, but discrete. Particles and waves blur into one another, and the idea that we can ever know the universe in complete detail becomes fundamentally impossible. One of the most profound phenomena in quantum mechanics is quantum fluctuations. Even in the emptiest reaches of space, where no stars shine and no gas clouds drift, the vacuum is never truly empty. Instead, it's seethes with transient particles that flicker in and out of existence in accordance with Heisenberg's uncertainty principle. These fluctuations are tiny, ephemeral blips of energy that exist for brief moments, yet they collectively shape the universe at both the microscopic and macroscopic scale. In the early universe, quantum fluctuations were magnified by cosmic inflation, seeding the density variations that would eventually form galaxies, clusters, and the cosmic web. Without these imperceptible fluctuations, the universe might have remained a featureless expanse, and the very structures that define the observable cosmos would never exist. Quantum mechanics also introduces the mind-bending phenomenon of entanglement, in which particles separated by vast distances remain mysteriously connected. When two particles are entangled, the measurement of one instantaneously determines the state of the other, regardless of how far apart they are. This spooky action at a distance, as Einstein famously described it, suggests that the universe has hidden threads linking distant points, a network of connections invisible to classical observation. At cosmic scales, entanglement challenges our assumptions about locality, causality, and the nature of edges. The universe's boundaries, defined by light travel and expansion, may not be absolute in the quantum sense. Information could, in principle, be correlated across regions that are otherwise disconnected, hinting that the edges of reality are fuzzier and more interconnected than they appear. The uncertainty principle introduces a fundamental limit to knowledge. At the smaller scales, one cannot simultaneously know a particle's exact position and momentum. Energy and time also obey similar constraints, meaning that fluctuations in energy can spontaneously occur over brief intervals. This principle has direct implications for cosmic boundaries. The edge of the observable universe, defined by the limit of light travel, is not a fixed line, but a region subject to quantum uncertainty. Particles and fields near this horizon fluctuate in ways that are fundamentally unpredictable. The universe is not a static container with neatly defined limits. It is a probabilistic landscape where boundaries are smeared by the intrinsic uncertainty of quantum processes. Quantum mechanics also reshapes our understanding of space and vacuum. Classical physics envisions empty space as inert and uniform, a simple stage upon which matter acts. Quantum physics reveals that the vacuum itself is dynamic, a sea of virtual particles, energy fluctuations, and fields that are never truly at rest. Even in the farthest reaches of intergalactic voids, this quantum activity persists, subtly influencing the distribution of matter and the behavior of radiation. The emptiness beyond observable galaxies is, in reality, a dynamic substrate, constantly fluctuating, full of energy that can never be entirely measured or predicted. This means that the edge of the universe is not a boundary of nothingness. It is a limit defined by our capacity to measure and interact with a restless quantum sea. The probabilistic nature of quantum mechanics transforms our conception of reality. Objects do not have definite states until measured. Waves collapse into particles only under observation. Events do not occur in a single deterministic pathway, but exist as a spectrum of possibilities. When applied to the universe at large, these principles suggest that the cosmos itself is fundamentally uncertain at its boundaries. The regions beyond our observation, beyond the cosmic microwave background, exist as possibilities rather than certainties. Light from these regions has not reached us, yet quantum principles imply that even there, fluctuations persist, shaping matter and energy in ways we may never directly witness. Quantum fluctuations also interact with gravity, especially near extreme environments such as black holes or the early universe. At singularities and the cosmic horizon, space-time itself is subject to uncertainty, creating a blur between what is inside and what is outside, between what can be observed and what remains hidden. These effects hint that the concept of an edge, whether of a galaxy, a black hole, or the universe itself, is not absolute. Instead, edges are probabilistic, shaped by the interplay of quantum mechanics and general relativity. Reality at cosmic scales is not what it seems. Boundaries are porous. Information can be encoded in subtle correlations, and space-time itself is a dynamic participant in the uncertainty. The implications for life, matter, and cosmic structures are profound. Quantum processes govern the formation of stars, the fusion reactions in stellar cores, and the decay of particles. Even the chemistry necessary for life depends on quantum effects, such as tunneling, which allows electrons to pass through energy barriers they could not overcome classically. At the edge of the universe, where energy is sparse and radiation is redshifted, quantum phenomena dominate, creating subtle currents of possibility that guide the evolution of matter and energy over billions of years. Structures that appear static on human scales are shaped continuously by invisible, fluctuating quantum forces. Quantum entanglement also redefines cosmic connectivity. Regions of space that seem isolated by the expansion of the universe may retain hidden links through entangled states, correlations that are preserved even across light years of distance. This challenges classical ideas about the observable horizon. While photons define the limit of what we can see, entanglement hints that information and correlation may extend beyond our measurement, tying together parts of the cosmos in ways that remain invisible but real. The universe may be a network of edges and connections, where what is beyond observation is still entangled with what is observable, a hidden continuity across apparent boundaries. Even the vacuum energy, the subtle energy present even in empty space due to quantum fluctuations, contributes to cosmic dynamics. Dark energy, which drives the accelerated expansion of the universe, may itself arise from these quantum effects. If so, the very edges of space are shaped not only by expansion, but by the restless energy inherent in the vacuum. The universe is never truly empty, and its boundaries are not static. They are influenced by the probabilistic, fluctuating energy of quantum mechanics, a reminder that reality is a complex, dynamic tapestry rather than a fixed stage. Quantum mechanics also intersects with the concept of cosmic horizons in ways that redefine our understanding of observation. Photons from the farthest reaches of space are limited by light speed, but the quantum vacuum is not constrained in the same way. Virtual particles appear and vanish even beyond these horizons, and entanglement may link events across distances that classical physics would treat as causally disconnected. The edges of the observable universe are, in effect, fuzzy, smudged by uncertainty and quantum connectivity. Reality at these scales is probabilistic, dynamic, and interconnected in ways that defy classical intuition. Quantum mechanics challenges the very notion of deterministic reality at cosmic scales. The universe is not a clockwork machine with fixed positions and trajectories. It is a realm of probability waves, fluctuating energy, and subtle correlations. The edges of the cosmos, like the space near black holes or the limits of observation, are not absolute walls, but regions defined by the interplay of uncertainty, fluctuation, and correlation. Reality is not a static stage, but a dynamic, probabilistic continuum where observation itself shapes what can exist and what can be measured. The cosmos, at its edges, is both stranger and more intricate than we can fully comprehend, a testament to the enigmatic, foundational principles of quantum mechanics. General relativity versus quantum physics. The universe is a place of extremes, where matter, energy, and space-time collide in ways that challenge even the most sophisticated theories. At one end of the scale, general relativity describes the curvature of space-time, the bending of light, and the gravitational dance of planets, stars, and galaxies. At the other, quantum physics governs the smaller scales where particles flicker in and out of existence. Uncertainty dominates, and entanglement defies classical logic. Both frameworks are incredibly successful in their domains, yet where they meet, inside black holes, near cosmic singularities, and at the earliest moments after the Big Bang, they clash. The universe at its edges, at its most extreme points, exposes the cracks in our understanding, revealing that the cosmos is far stranger than our models can fully capture. Einstein's general relativity redefined gravity, not as a force acting across space, but as the curvature of space-time itself. Massive objects bend the fabric of reality, causing planets to orbit stars, light to curve around galaxies, and time itself to slow near immense gravitational wells. These principles accurately describe everything from the motions of planets to the expansion of the universe. Gravitational lensing allows us to map distant galaxies. Black holes are predicted with precise mass and spin, and cosmic expansion follows the equations of general relativity with remarkable precision. This framework paints the universe as a smooth, continuous manifold where energy and mass dictate the geometry of space-time. Quantum physics, in contrast, describes the universe as inherently discrete. Energy, momentum, and even space itself exhibit granularity. Particles exist in superpositions. States remain uncertain until measured, and fields fluctuate constantly. Quantum mechanics successfully explains atomic structure, particle behavior, and interactions at the smaller scales. The entire standard model of particle physics rests on these principles, describing forces and matter with unparalleled accuracy in laboratory settings. Light, electromagnetism, and the interactions that govern chemistry and biology all obey quantum rules. The conflict arises when general relativity and quantum physics intersect. Singularities, such as those at the center of black holes or at the origin of the universe, represent regions where densities become infinite, curvature diverges, and the classical equations of relativity fail. At these points, general relativity predicts infinite energy density and a breakdown of space-time itself. Yet quantum mechanics dictates that uncertainty and fluctuations dominate, preventing absolute precision. The two frameworks describe reality in incompatible ways. Relativity assumes continuity, determinism, and smoothness, while quantum physics embraces probabilistic fluctuations, discrete states, and fundamental limits on measurement. Cosmic singularities are the ultimate edges of the universe. They are points where conventional physics cannot describe what exists. The center of a black hole, for instance, represents a singularity where space collapses to zero volume. Time may cease in any conventional sense, and the known laws of physics provide no meaningful predictions. Similarly, the Big Bang represents a singularity in reverse. The universe begins as a point of infinite density, from which space, time, and energy emerge. At these boundaries, the universe exposes its ultimate limits, the edges of understanding, and the points where the smooth fabric of general relativity meets the jittering uncertainty of quantum mechanics. Efforts to reconcile these two frameworks have led to theories of quantum gravity, string theory, and loop quantum gravity, yet none are experimentally confirmed. The challenge is profound. How can a framework based on continuity and curvature coexist with one based on probability and discreteness? Singularities become laboratories for thought experiments, revealing the extreme conditions that the universe can sustain. They are not merely mathematical curiosities. They are the points where the universe itself confronts the limits of knowledge. time behaves differently under these extremes. Near a black hole's singularity, relativity predicts that time stretches infinitely relative to distant observers. Yet quantum uncertainty introduces fluctuations in energy and particle states that may alter the evolution of space-time itself. The intersection of these effects suggests that the edges of the universe and the boundaries of space-time are far more complex than smooth curves or simple event horizons. They are probabilistic, fluctuating, and potentially interconnected in ways that defy classical description. General relativity describes cosmic expansion as a smooth stretching of space. Yet at the quantum level, the vacuum is restless, filled with fluctuations that create energy density, virtual particles, and even subtle forces that can affect large-scale dynamics. Dark energy, which drives accelerated expansion, may originate from these quantum fluctuations, highlighting the interplay between the micro and the macro, between the discrete jitter of particles and the smooth geometry of the cosmos. At the edge of observation, this interplay defines what can exist, what can be observed, and what remains fundamentally uncertain. Black holes exemplify the breakdown of classical and quantum frameworks. Inside the event horizon, relativity predicts inevitable collapse, while quantum mechanics forbids the destruction of information. Hawking radiation, quantum tunneling, and entanglement suggest that black holes are not isolated voids, but dynamic systems where information and energy continue to interact with the outside universe. These edges, event horizons, and singularities reveal that the universe's boundaries are not static walls, but regions where different physical rules compete, fluctuate, and redefine the limits of reality. Cosmic singularities also challenge the notion of causality. Near these extremes, space-time can curve to such an extent that conventional sequences of cause and effect become distorted. Quantum fluctuations further complicate the picture, introducing randomness into regions that relativity would treat as deterministic. The universe's edges are therefore not merely distant points in space. They are arenas where time, causality, energy, and information are intertwined in ways that make classical intuition meaningless. The early universe provides another illustration of this tension. During the first fractions of a second, densities were so extreme that quantum fluctuations in energy and fields dominated the behavior of space-time. Inflation stretched these fluctuations across the cosmos, seeding galaxies and clusters. Relativity describes the large-scale stretching of space, but the quantum behavior of energy at these tiny scales set the initial conditions for cosmic structure. The edge between quantum uncertainty and relativistic smoothness produced the universe as we see it today, a dynamic interplay that continues to shape cosmic evolution billions of years later. Gravitational waves add further insight into these extremes. Generated by colliding black holes or neutron stars, these ripples in space-time provide evidence of general relativity at work. Yet the precise quantum states of the merging objects introduce subtle uncertainties. The edges of observation, defined by the speed of light and horizon distances, are filled with these waves, carrying energy and information that challenge classical expectations. Each gravitational wave signal is a record of the interaction between relativistic curvature and quantum uncertainty, a testament to the complexity at cosmic edges. The tension between general relativity and quantum physics also influences the ultimate fate of the universe. Energy conservation, entropy, and expansion are described by classical physics, yet quantum fluctuations, vacuum energy, and probabilistic behavior shape the conditions at extreme scales. The edge of space-time may be defined not by a physical boundary, but by limits imposed by the interplay of these frameworks. Regions beyond our observational horizon exist, but quantum effects suggest subtle interactions or correlations that could extend influence in ways we cannot measure. Space-time curvature near singularities, event horizons, and the expanding edge of the universe highlights the limits of measurement and prediction. Mass, energy, and momentum remain fundamental, yet uncertainty and fluctuations challenge the determinism assumed by classical relativity. Observers are constrained by horizons, redshifted photons, and gravitational effects, while quantum processes allow information and energy to persist in unexpected ways. The boundaries of the cosmos are therefore dynamic, defined by competing principles, and always probabilistic rather than absolute. The conflict between general relativity and quantum physics underlines a central truth about cosmic edges. The universe does not conform neatly to human models. Singularities, black holes, and the earliest moments of cosmic expansion are real, extreme phenomena that exist precisely at the limits where our understanding breaks down. These edges are not abstract. They are places in space and time where energy, matter, and information interact under conditions far beyond everyday experience. The universe contains layers of boundaries, relativistic horizons, event horizons, and the cosmic microwave background define edges of observation and influence. Quantum uncertainty and entanglement blur these edges, creating regions where matter and energy persist in states inaccessible to classical measurement. The interplay between smooth curvature and probabilistic fluctuation ensures that cosmic boundaries are both real and elusive, concrete in their effects, yet subtle in their limits. At every scale, the universe demonstrates that edges are not simple walls, but regions of complexity. Singularities represent limits of current theory, where density, gravity, and curvature diverge. Quantum mechanics ensures that no edge is truly static, as fluctuations, entanglement, and uncertainty introduce dynamism even in otherwise inert regions. Energy, information, and causality are conserved, yet the manifestation of physical laws at these edges is profoundly altered, revealing the universe as a realm of paradox, extremity, and astonishing subtlety. The universe as a multiverse. The universe we observe is immense, far beyond the reach of the human eye, extending billions of light years in every direction. Galaxies, clusters, and filaments stretch across space in an intricate web, while the cosmic microwave background glows faintly as a relic of the Big Bang. Yet as vast as this observable universe seems, physics suggests that what we see may only be a fraction of a far larger reality. Beyond the limits imposed by light, time, and causality, there may be regions, realms, or even entirely separate universes that lie forever beyond direct observation. The notion of a multiverse, a collection of universes each with its own physical laws and boundaries, forces us to reconsider what an edge truly means. Are the limits we perceive merely a local boundary, a horizon defined by the speed of light and the expansion of space? Or is the universe infinite, continuous, and layered with realities we cannot yet access? The concept of a multiverse emerges naturally from cosmic inflation, the rapid exponential expansion that occurred in the first fraction of a second after the Big Bang. During inflation, space itself stretched at unimaginable rates, smoothing out irregularities while magnifying quantum fluctuations into macroscopic structures. Some models suggest that this expansion was not uniform everywhere. In different regions, inflation may have continued longer or shorter, producing bubble universes, distinct domains where the energy density, physical constants, or even the number of dimensions differs. Each bubble could evolve independently, separated by space-time regions that expand faster than light can traverse. In this scenario, the universe we see is just one bubble among countless others, a single local patch in an infinitely layered cosmic expanse. Within the multiverse framework, the concept of an edge becomes fundamentally ambiguous. Our observable horizon is limited by the speed of light and the finite age of the universe, 13.8 billion years. Light emitted beyond this horizon has not had time to reach us, and due to cosmic expansion, much of it may never arrive. Yet beyond this observable horizon, matter, energy, and possibly entire universes continue to exist, unobserved but real. What we perceive as the edge of the universe is therefore not a boundary of existence, but a horizon of observation. The universe may extend infinitely, yet our access is confined by causality and the physical properties of space-time. Even within a single universe, observable limits define what can interact with us. The cosmic horizon is a boundary imposed by the combination of light speed and the age of the universe. Galaxies beyond this horizon exist, yet their light cannot reach us because space expands faster than the light can traverse it. In a sense, every observer has a personal edge, a horizon beyond which the universe is causally disconnected. The expansion of space ensures that this horizon grows over time, but some regions recede so quickly that they will remain forever beyond view. These edges are not physical walls. They are limits of information, defined by the laws of physics rather than the distribution of matter. The question of absolute limits versus observable limits extends to the very structure of space-time. Light provides the maximum speed for causal interaction, setting a universal limit on how far information can travel. Yet quantum mechanics complicates this picture. Entanglement allows correlations between particles separated by vast distances, suggesting subtle connections that operate beyond classical horizons. Vacuum energy, fluctuations, and zero-point fields pervade space, existing even in regions beyond observation. In this way, edges defined by light are local illusions. Energy and correlation persist, but our capacity to measure or interact is constrained. If the universe is indeed part of a multiverse, then edges become even more illusory. Bubble universes may collide, interact, or remain entirely separate, each with its own horizon. In such a framework, an edge is a region where local laws appear to stop, but a larger structure continues. What we perceive as an endpoint of space might be just a boundary within a more complex system of multiple universes, where other realms exist with different dimensions, constants, and forms of energy. The edge of one universe could be the interface with another, a boundary that is only locally significant. Cosmic inflation also provides a mechanism for creating effectively infinite space. Even within our bubble, expansion stretches regions far beyond our observable limits, creating an environment where the concept of a physical edge becomes meaningless. The universe may be flat or curved in ways that we cannot measure directly, yet in either case, space continues without termination. Regions that recede faster than light exist beyond interaction, but remain part of the same cosmic continuum. These superluminally expanding regions highlight the difference between what exists and what we can perceive, a fundamental distinction when discussing cosmic edges. The multiverse hypothesis also raises questions about the nature of physical law. Different bubble universes could operate under different constants, particle masses or forces. Electromagnetism, gravity, or quantum rules might vary, creating universes with radically different behaviors. In such contexts, what appears as an edge in one universe might be a transition zone to another with different physical realities. The boundary is no longer a termination point of existence, but a local interface shaped by physics, energy, and space-time conditions. Our edge becomes a window, not a wall. The observable limits also define practical boundaries for human exploration. Even if matter and energy exist beyond our horizon, reaching these regions may be impossible. Expansion ensures that distant galaxies recede faster than light, and cosmic acceleration driven by dark energy will increase this separation over time. No rocket, signal, or probe could traverse these distances. For all intents and purposes, these regions are forever outside our causal domain, even though they exist. In this sense, edges are both real and illusory. They define what we can influence and observe, yet they do not define what exists. Quantum fluctuations further blur the line between local and absolute edges. Even in regions beyond observation, particles and fields continue to exist probabilistically, fluctuating in energy and position. Zero-point energy and vacuum fluctuations provide activity in otherwise empty space, hinting that the universe is never entirely quiescent. These fluctuations may influence large-scale structure through inflation, gravitational interactions, or dark energy. The cosmic edge, then, is a region where observability ceases, but underlying physical processes persist, maintaining continuity beyond the horizon of perception. Causality also shapes the concept of edges. Information travels at the speed of light, establishing the observable horizon for any point in space-time. Beyond this horizon, events cannot influence the observer. However, expansion, quantum entanglement, and vacuum energy suggest that the universe is interconnected in subtle ways. The edge we perceive is therefore a local phenomenon, defined by measurement, observation, and causality, rather than a fundamental limit of existence. What lies beyond may be forever unreachable, yet it is not absent. The possibility of other universes challenges our understanding of infinity and boundaries. If multiple universes exist, separated by space, energy, or dimensional differences, the universe we see is just one manifestation of a larger reality. The edge of our universe becomes a local horizon, and the cosmic horizon itself is a subset of a broader structure. Edges are thus contextual, dependent on both local physics and the broader multiverse. Each universe may have its own rules, its own horizons, and its own limitations. Yet collectively, they form a continuum where existence is far more expansive than perception allows. Observable limits and absolute limits intersect in unexpected ways. Light speed establishes the maximum range of observation, defining a practical edge. Dark energy drives accelerated expansion, ensuring that some regions will always remain beyond reach. Quantum mechanics introduces uncertainty, fluctuations, and non-local correlations, suggesting hidden continuity. Cosmic inflation produces bubble universes, potentially with distinct laws and dimensions. All these factors combine to illustrate that edges are multifaceted. They exist in observation, in physics, and in structure, yet they do not necessarily define the totality of existence. Even concepts such as cosmic time and the age of the universe contribute to the notion of edges. The universe is 13.8 billion years old, meaning light from the earliest galaxies has only travelled so far. Yet expansion stretches this distance, so that galaxies currently exist far beyond where their light can reach us. Our cosmic horizon is therefore dynamic, shaped by both temporal and spatial factors. What we see is a fraction of what exists, and the rest, though real, remains inaccessible. The interplay of cosmic inflation, light speed limits, dark energy, and quantum uncertainty suggests that the universe's edges are apparent rather than absolute. Regions beyond observation are real, but practically unreachable. Bubble universes may exist with independent physics. Horizons defined by causality constrain influence but not existence. Quantum fields fluctuate in all space, connecting regions subtly. The universe, in this view, is a vast, layered, probabilistic system where edges are defined by perspective, measurement, and interaction, rather than by termination of matter, energy, or space. Edges may therefore be local illusions. observers within a single universe perceive a horizon shaped by light, expansion, and observation. Beyond this horizon lies more space, more matter, possibly more universes. The end of the universe is never truly an end. It is a boundary of perception, a limit to causal influence, and a marker of what we can measure. Absolute existence continues beyond, layered and dynamic, revealing that the cosmos may be more expansive and more interconnected than any single horizon suggests. The multiverse concept also reframes questions about the fine-tuning of the universe. If other universes exist with different constants, the apparent precision of physical laws in our universe may be a local phenomenon, determined by the subset of conditions where observers can exist. In such a scenario, edges of observation are tied not just to physics, but to the anthropic conditions that allow life and measurement. Beyond our universe, different edges and horizons may define entirely different realities, highlighting that the edge is a perspective rather than a definitive boundary. Cosmic acceleration driven by dark energy ensures that more distant regions of space will eventually cross our horizon, disappearing from view permanently. These regions exist but become causally disconnected. The edge of observation moves dynamically as expansion continues. Quantum fields and vacuum energy persist in these unreachable regions, yet practical interaction is lost. This reinforces the idea that edges are multifaceted. Some are horizons of light and causality, some are boundaries imposed by local energy conditions, and some may be transitions to entirely separate universes. The interplay between the observable and the absolute defines the ultimate scope of cosmology. Observation is limited by light, time, and expansion. Absolute existence extends beyond observation, shaped by quantum mechanics, energy conservation, and possible multiverse structure. The universe appears finite from our perspective, yet it may be infinite in extent and diverse in structure. Every horizon is both real and illusory, a marker of what can influence us, not a termination of reality. In this context, reaching the edge may be physically impossible. Cosmic expansion, light speed limits, and quantum uncertainty guarantee that some regions will remain forever inaccessible. Yet these regions exist, fluctuate, and influence the universe in subtle ways. Edges are therefore not fixed walls, but dynamic, probabilistic boundaries shaped by both local physics and broader cosmic structure. The big picture emerges. The universe is far more expansive, layered, and interconnected than simple observation allows. Multiverse models, inflationary theory, and quantum mechanics suggest that what we perceive as edges are local, practical, and dynamic. Beyond our horizon lies more space, more energy, possibly other universes. Observability defines one set of limits, but absolute existence continues, subtle, vast, and in some sense, unknowable. Edges are therefore boundaries of perspective, not termination, reminding us that the cosmos is larger, stranger, and more profound than perception alone can capture. Reality is not what it seems. The universe we experience is not the universe that exists. Our senses, our instruments, and even our most advanced telescopes capture only a fraction of the cosmic story. What we see, light from stars, the glow of galaxies, the faint relic of the Big Bang, is just a thin veneer atop a far deeper, stranger reality. The majority of the universe remains invisible, hidden from direct observation, yet it dominates the dynamics of space, time, and matter. Our perception is filtered, limited, and localized, and the cosmos beyond our instruments is governed by forces and phenomena that are largely unknown. To understand the universe in its totality, we must confront the possibility that reality is not what it seems. One of the most striking examples of this hidden universe is dark matter, an invisible substance that outweighs visible matter by a factor of 5. Dark matter does not emit, absorb, or reflect light, yet its gravitational influence is unmistakable. Galaxies rotate at speeds that cannot be explained by visible mass alone. Clusters of galaxies bend light in ways inconsistent with observable matter. And cosmic structure, filaments, voids, and the large-scale web, is shaped predominantly by this unseen component. We do not see dark matter directly. We only infer its existence from the effects it has on objects we can observe. The universe that we perceive, luminous and structured, is therefore only the tip of a vast invisible scaffold, one that defines motion, formation, and the architecture of reality itself. Even more mysterious is dark energy, a force driving the accelerated expansion of the universe. Unlike gravity, which pulls matter together, dark energy pushes space apart, acting uniformly across the cosmos. It constitutes roughly 70% of the total energy density of the universe, yet we know almost nothing about its nature. We can measure its effect by observing the recession of galaxies, but the substance itself remains elusive, an invisible presence shaping the ultimate fate of all cosmic structures. Together, dark matter and dark energy dominate the universe, meaning that the luminous cosmos, the galaxies, stars, and planets we can see, comprises less than 5% of what actually exists. Reality at the cosmic scale is therefore profoundly counterintuitive. What dominates the universe is not visible, and what is visible is a minor, localized exception. Perception is further limited by the observable horizon. The speed of light and the finite age of the universe constrain what we can detect. Galaxies beyond this horizon exist, yet their light has not had time to reach us. Expansion ensures that many regions are receding faster than light, rendering them forever inaccessible. The cosmos we can see is therefore a local bubble of causality, a window into a much larger structure. The boundary of our perception is not an edge of existence. It is an observational horizon, defined by the interplay of light, space, and time. Beyond it lies reality that may be entirely unlike what we assume, shaped by unseen forces, vast stretches of emptiness, and cosmic energy we cannot measure. The universe is also filled with hidden energy fields and phenomena that challenge our understanding of matter. Quantum fields permeate all space, even the emptiest voids, fluctuating constantly and giving rise to transient particles. These fluctuations, imperceptible in day-to-day experience, influence cosmic evolution. The vacuum is not empty. It is a dynamic, restless medium, and what appears as nothingness is in fact a seething landscape of energy and possibility. The universe that seems static or empty is therefore far from quiescent. Reality is dynamic at all scales, and the familiar solidity of matter is an illusion, arising from interactions between fundamental particles and fields shaped by laws we barely comprehend. The hidden nature of reality raises profound questions about our location in the cosmos. Could we exist at a boundary and not know it? The observable universe is finite in extent, yet the full cosmos may be far larger, perhaps infinite, and may contain regions completely isolated from us. The very structure of space-time, warped by gravity and defined by cosmic expansion, means that causal contact with certain regions may be impossible. It is conceivable that our local patch of the universe is adjacent to extreme regions, voids, bubbles of separate universes, or domains dominated by strange physics. And yet we would remain unaware. Our perception, bound by light, instruments, and local physics, may give the impression of uniformity, where the universe is actually far more exotic. The mismatch between perception and reality is amplified by cosmic scales. Distances in space are so vast that light traveling from distant galaxies takes billions of years to reach us. By the time we see these objects, we observe them as they were long ago, not as they are now. The present universe is therefore unknowable in direct observation. What we see is always a historical echo. Our perception is not just partial, it is delayed, filtered by the finite speed of information. The apparent uniformity of the cosmos masks dynamic processes, extreme energies, and unseen structures that lie beyond our horizon of detection. Even fundamental concepts like matter, mass, and energy are not as straightforward as they seem. Observation suggests that most matter is invisible, most energy is unmeasured, and the space itself is dynamic and filled with latent forces. Gravity, a force we can feel on Earth, acts across cosmic distances in ways that reveal invisible matter and energy. Light bends around massive objects, revealing concentrations of mass we cannot see directly. The universe is therefore a complex tapestry of forces, energy, and matter, with perception capturing only a narrow thread of the total pattern. What we interpret as edges, voids, or structures may be illusions produced by incomplete information and selective visibility. Quantum mechanics further complicates cosmic perception. Particles exist in superpositions, states remain uncertain until measured, and entanglement links distant regions in ways that classical intuition cannot explain. The universe behaves probabilistically at fundamental scales, meaning that even where we can observe phenomena, the underlying reality may differ from expectation. Cosmic boundaries, horizons, and voids are therefore not absolute. They are influenced by quantum uncertainty, energy fluctuations, and non-local correlations. Reality is probabilistic, dynamic, and layered, with observable phenomena only representing one facet of a deeper, more complex cosmos. The concept of edges in the universe is therefore deeply intertwined with perception. Observational limits define practical edges, but not absolute ones. Beyond the cosmic microwave background, beyond receding galaxies, beyond the observable horizon, the universe continues. Space may stretch infinitely, filled with energy and matter, and possibly other domains governed by different physical constants. What seems like an edge may be an artifact of our observational tools, our position in space, and the speed of light. The universe may be a seamless continuum, with apparent boundaries arising from limits in perception rather than from the cessation of existence. Unseen forces, fluctuations, and cosmic energy also shape life and matter at subtle levels. From the behavior of atoms to the formation of galaxies, unseen phenomena govern structure, motion, and evolution. Gravity, dark matter, and dark energy orchestrate cosmic architecture, while quantum fields underlie chemical bonds, nuclear reactions, and the stability of matter. What we perceive as reality, the glowing stars, planets, and visible matter, is a local manifestation, a thin layer atop an invisible scaffold of energy and forces that dominate the universe. The majority of existence is hidden, yet it dictates what can exist, move, and interact. Cosmic expansion emphasizes the divide between perceived and absolute reality. Galaxies are receding, and the rate of expansion means that regions will eventually become causally disconnected. Light emitted from these regions will never reach us. Our edge of observation is therefore a horizon, not a wall. Beyond it, energy, matter, and possibly entirely new universes exist, yet they remain inaccessible. The universe is larger, more interconnected, and more dynamic than perception alone suggests. The universe also challenges notions of dimensionality. While humans perceive 3 spatial dimensions and 1 temporal dimension, physics allows for extra dimensions, compactified or extended, which influence forces and particle interactions. These hidden dimensions may shape the universe in ways invisible to our instruments, further separating perception from underlying reality. The edges we perceive, the structure we map, and the forces we measure are therefore only partial reflections of a deeper, multidimensional cosmos. Dark energy and dark matter illustrate how dominant forces can be invisible. Dark matter structures the universe's cosmic web. Dark energy drives accelerated expansion. Both remain undetectable directly. What we see, the stars, galaxies, and luminous matter, is therefore not representative of the whole universe. The majority of existence is hidden, yet it governs motion, gravity, and cosmic evolution. Observational perception captures only a fraction of reality, creating a universe that is apparent rather than absolute, local rather than global, and incomplete rather than total. The notion of existing at a boundary without awareness becomes plausible when considering these unseen elements. Cosmic horizons, expansion, quantum fluctuations, dark matter, and dark energy all define limits to observation. Within these limits, perception may create the illusion of a complete, coherent universe. Yet outside these boundaries, reality continues, structured by forces we cannot detect, shaped by energy we cannot measure, and possibly connected to domains we cannot access. Our experience of space, time, and matter is therefore a local perspective, one that may be far from the full cosmic truth. Reality at cosmic scales is also dynamic and evolving. Structures change, stars form and die, galaxies collide, and cosmic voids expand. Quantum fluctuations, dark energy, and gravitational interactions continue to shape the universe in ways invisible to observers. Even what seems static, empty space, is a stage of constant activity. The universe is therefore not a static backdrop, but a living, fluctuating system, where perception captures only snapshots and illusions of continuity. Cosmic perception is also temporal. The universe is 13.8 billion years old, meaning observation is always of the past. The light from distant galaxies reveals conditions long ago, and expansion ensures that many regions will never be observed. Our edge is therefore defined not only by distance, but by time. The universe beyond this temporal horizon continues, but remains forever unobserved. Perception is thus constrained both spatially and temporally, creating local illusions of completeness and edges. Finally, cosmic reality challenges assumptions of uniformity and structure. What appears as homogeneous on large scales may hide vast complexity. Voids, filaments, and clusters are shaped by forces and matter invisible to our instruments. Local measurements, limited by light and causality, cannot reveal the totality of cosmic connections. The universe is far richer and stranger than perception allows, and what we see is only a small, filtered subset of the full reality. Reality is therefore not what it seems. Observation captures light, matter, and structure, yet invisible forces dominate. Edges appear, horizons define limits, and unseen energy structures cosmic evolution. We may exist at a boundary without knowing it, surrounded by forces, energy, and space beyond perception. The universe is more immense, layered, and interconnected than we can measure. A dynamic, probabilistic, and largely hidden reality that far exceeds the illusions of perception. Future exploration. The quest to understand the universe is far from complete. Humanity has only begun to scratch the surface of cosmic reality, peering into the depths of space with telescopes, mapping gravitational waves, and probing quantum phenomena that shape the very fabric of existence. Each new generation of observation pushes the boundaries of what we know, revealing not just distant galaxies and stars, but the fundamental workings of space, time, energy, and matter. Future exploration promises to take us further than ever before, probing the universe in ways that challenge our perception, extend our reach, and test the limits of physical law. Telescopes have revolutionized our view of the cosmos. The Hubble Space Telescope transformed astronomy by providing unprecedented clarity, revealing galaxies billions of light years away and mapping the large-scale structure of the universe. Its images show the vast web of filaments, clusters, and voids that compose the cosmic landscape, giving us a glimpse of the scale and complexity of the universe. Hubble has also provided critical measurements of cosmic expansion, supernova events, and the distribution of matter, including the gravitational influence of dark matter. By observing light that has traveled for billions of years, Hubble allows us to peer into the past, reconstructing the early universe and testing models of formation, evolution, and cosmic structure. The James Webb Space Telescope, JWST, takes this exploration further, extending our reach into the infrared, where the earliest galaxies and stars reveal themselves. By capturing faint signals from the first few 100 million years after the Big Bang, JWST enables direct study of the universe's formative stages. It provides insight into star formation, the assembly of galaxies, and the distribution of matter during the epoch of rhyonisation. Observing these primordial structures allows scientists to test predictions of cosmological models, understand the role of dark matter and dark energy, and explore the origins of cosmic filaments that shape the large-scale structure. Webb's advanced instruments reveal not only distant galaxies, but also the chemical composition of exoplanet atmospheres, offering a window into the potential habitability of worlds across the universe. Future telescope missions promise even greater discoveries. Concepts such as the Nancy Grace Roman Space Telescope and LUVOIR, Large Ultraviolet Optical Infrared Surveyor, aim to provide wider fields of view, higher resolution, and enhanced sensitivity to faint cosmic signals. These instruments will map the universe in unprecedented detail, studying dark energy, galaxy evolution, and the distribution of matter across vast scales. Ground-based projects like the Extremely Large Telescope, ELT, and the 30-metre telescope, TMT, will complement space observatories by providing unparalleled resolution and light-gathering power, enabling precision measurement of cosmic phenomena. Together, these tools expand our observational horizon, pushing closer to the limits of what we can see and challenging the very notion of a cosmic edge. Beyond light, the universe reveals itself through gravitational waves, ripples in space-time generated by extreme events such as black hole mergers, neutron-star collisions, and the early moments of cosmic inflation. The detection of these waves by observatories such as LIGO and Virgo has opened an entirely new window into the cosmos. Unlike light, gravitational waves pass through matter almost unimpeded, carrying information about events that would otherwise be invisible. They allow us to probe the interior dynamics of massive objects, measure the expansion of the universe, and test general relativity under extreme conditions. Each detection reveals both the scale and complexity of the universe, offering insight into the behavior of matter, energy, and space-time at the edges of known physics. Future gravitational wave observatories, including LISA, Laser Interferometer Space Antenna, promise to extend these studies to lower frequencies, capturing waves from supermassive black hole mergers and potentially even primordial waves from the Big Bang. These instruments will provide a map of space-time itself, revealing the geometry, curvature, and fluctuations of the cosmos across immense scales. Gravitational wave astronomy is not just a new way to observe. It is a fundamental tool for probing the limits of physical law, testing theories of gravity, and exploring regions that are otherwise inaccessible to light-based instruments. Quantum experiments are also pushing the boundaries of cosmic understanding. Quantum mechanics governs the smallest scales, yet its effects extend into the structure of the universe itself. Experiments on entanglement, superposition, and quantum fluctuations provide insight into phenomena that shape cosmic evolution. By testing the behavior of particles and fields under extreme conditions, scientists probe the foundations of space-time, energy, and information. These studies have implications for dark energy, vacuum fluctuations, and even the nature of cosmic horizons. Quantum experiments may reveal subtle connections across vast distances, suggesting that reality itself is more intertwined and complex than classical observation allows. The interplay of telescopic observation, gravitational wave detection, and quantum experimentation creates a comprehensive framework for future exploration. Light-based telescopes allow us to see the structure of galaxies, clusters, and cosmic filaments. Gravitational waves probe the dynamics of extreme events and the curvature of space-time. Quantum experiments reveal the behavior of matter and energy at fundamental levels. Together, these approaches expand our understanding of both the observable universe and the hidden components that govern its evolution. Probing the universe also involves testing the limits of physics. Black holes, singularities, and the early universe present extreme conditions where general relativity and quantum mechanics intersect, and where our current understanding breaks down. Observations of event horizons, accretion disks, and relativistic jets allow scientists to examine gravity under the most extreme conditions, while quantum fluctuations provide insight into the origin of structure, vacuum energy, and the dynamics of inflation. By pushing the boundaries of measurement, experimentation, and observation, humanity seeks to reconcile the macroscopic laws of space-time with the microscopic rules of quantum physics. The cosmic microwave background, CMB, remains a critical tool for probing the universe. This relic radiation from the Big Bang carries information about the early universe, the distribution of matter, and the dynamics of expansion. Future missions aim to measure its polarization, temperature fluctuations, and spectral distortions with unprecedented accuracy. Such measurements test models of inflation, probe the density and distribution of dark matter, and constrain the properties of dark energy. By studying the faintest imprints in the CMB, scientists gain insight into the structure of the universe at its earliest moments, approaching conditions that define the cosmic edge. Advances in technology will also allow direct observation of exoplanets and distant systems, probing atmospheres, chemical compositions, and potential biosignatures. These observations provide context for understanding cosmic habitability, the formation of planetary systems, and the prevalence of life in the universe. The edges of our observational capabilities will expand beyond galaxies and clusters to encompass the chemistry of distant worlds, connecting the larger scales of the universe with the smaller structures that sustain life. The mapping of space-time through multi-messenger astronomy, combining light, gravitational waves, neutrinos, and cosmic rays, will revolutionize our understanding of cosmic boundaries. By correlating signals across different carriers of information, scientists can construct a more complete picture of structure, energy flow, and extreme phenomena. This approach reveals hidden connections, tests theoretical models, and uncovers interactions that single observation methods cannot detect. Multi-messenger exploration represents the next frontier in probing the universe, bridging the visible, hidden, and extreme domains of cosmic reality. Quantum sensors and precision instruments will extend humanity's reach even further. Devices capable of detecting minuscule fluctuations in energy, gravitational fields, or particle states can probe fundamental physics on cosmic scales. These tools may detect evidence of extra dimensions, vacuum energy fluctuations, or subtle interactions between matter and dark components of the universe. By testing the limits of measurement, scientists hope to uncover the underlying structure of reality, revealing aspects of the universe that are currently hidden from perception. The integration of observation, theory, and experimentation defines the future of cosmic exploration. Telescopes, gravitational wave observatories, and quantum experiments do not act in isolation. Together, they provide complementary perspectives on the universe. Observations reveal structure and dynamics. Waves trace energy and curvature. And quantum experiments probe the foundations of matter and space-time. This combined approach allows exploration of both the observable universe and the hidden dimensions, testing the boundaries of existence and extending human knowledge to regions previously unreachable. In addition to technical exploration, the future includes simulation and modeling of cosmic phenomena. Advanced computing allows scientists to simulate galaxy formation, dark matter distribution, and the evolution of space-time under extreme conditions. By combining observational data with theoretical models, researchers can predict phenomena beyond current observational limits, test hypotheses about the cosmic edge, and explore scenarios for the behavior of matter, energy, and space-time at extreme scales. These virtual explorations act as guides for future observation and experimentation, extending understanding beyond what is directly measurable. Ultimately, future exploration aims to answer fundamental questions. What is the structure of the universe beyond our horizon? Do other universes exist? How do space, time, and matter behave under extreme conditions? Can quantum mechanics and general relativity be unified? Can we probe the edges of space-time and understand the limits of existence? Each telescope launched, each gravitational wave detected, and each quantum experiment performed brings humanity closer to these answers, revealing the vast complexity, subtlety, and grandeur of the cosmos. The next generation of discoveries promises not only to extend human knowledge, but to challenge perception itself. Observing the first galaxies, mapping the cosmic web, detecting gravitational ripples, and probing quantum fluctuations will expand the universe we know. We may discover regions where physical laws differ, detect phenomena previously thought impossible, and redefine the meaning of edges and boundaries. The universe in its entirety is a dynamic, evolving, and layered reality, and future exploration is humanity's way of peeling back the layers to reveal the deeper truth. Cosmic exploration is therefore not just about mapping what exists, but about understanding the fundamental principles that govern existence. It is an attempt to bridge perception with reality, connecting the visible universe with hidden energy, dark matter, dark energy, and the extreme phenomena that shape the cosmos. Through telescopes, gravitational wave observatories, quantum experiments, and simulations, humanity probes both the edges of observation and the edges of understanding, revealing the intricate, layered, and astonishingly complex universe in which we exist. The universe we perceive is vast, yet it may be just one layer of an even greater reality. Future exploration will continue to expand this window, revealing regions beyond light, structures beyond comprehension, and forces beyond measurement. Every new discovery challenges assumptions, redefines limits, and uncovers new horizons. Humanity stands at the threshold of a profound journey, where observation, experimentation, and theory converge to explore the ultimate questions of cosmic existence. Future exploration is therefore a multi-dimensional endeavor, observing galaxies and clusters, detecting gravitational waves, probing quantum phenomena, mapping dark matter and energy, and testing the extremes of space-time. This pursuit will not only extend the boundaries of human knowledge, but redefine the concept of cosmic edges, revealing that what we perceive as the universe is merely a window into a far more vast, hidden, and dynamic reality. Human understanding at the edge. The universe stretches far beyond anything we can directly observe, a vast expanse of galaxies, clusters, voids, and filaments, expanding and evolving over 13.8 billion years. Human understanding, however, has limits, not of curiosity, but of observation, measurement, and interaction. Telescopes reveal distant galaxies, gravitational waves trace ripples in space-time, and quantum experiments probe the foundations of matter and energy. Yet each instrument, no matter how sophisticated, confronts boundaries imposed by physics itself: the speed of light, cosmic expansion, quantum uncertainty, and the sheer scale of space. Science allows us to map, measure, and predict. But there are regions, phenomena, and scales where even the most advanced experiments reach their limits. The observable universe is defined by what light and information have had time to reach us. Galaxies beyond the horizon exist, yet their signals cannot traverse the expanding space to arrive at our instruments. The cosmic microwave background marks the earliest light we can see, a relic from 380,000 years after the Big Bang, beyond which we cannot observe directly. Even here, the universe was opaque, filled with a dense plasma that trapped photons, so the surface of last scattering forms, a cosmic boundary for visual observation. We are always looking at a past we cannot fully reach, a universe whose present configuration remains partially hidden. Human understanding, then, is constrained by time as well as space. Yet our knowledge is not entirely passive. Gravitational waves offer a new lens, revealing cosmic events invisible to light-based observation: black hole mergers, neutron star collisions, and possibly primordial vibrations from the earliest moments of inflation. These waves traverse space unimpeded, carrying information about the dynamic universe, probing structures and processes that lie beyond our direct vision. Future missions like LISA will expand this capacity, mapping the curvature of space-time and exploring phenomena at scales we have only theorized about. Through these observations, science pushes ever closer to the limits of what is knowable, extending understanding to regions and events that were once purely speculative. Quantum experiments further probe the edge of understanding. Entanglement, superposition, and quantum fluctuations challenge classical notions of locality, causality, and determinism. Laboratory studies of quantum mechanics provide insight into phenomena that govern the early universe and cosmic structure. Fluctuations in the vacuum during inflation may have seeded the formation of galaxies and cosmic filaments, demonstrating how microscopic uncertainties influence the macroscopic universe. At cosmic scales, quantum behavior interacts with gravity, producing singularities, black hole event horizons, and extreme energy regimes. These are regions where current theories break down, where general relativity and quantum mechanics clash, and where the universe reveals its deepest mysteries. Human understanding approaches these frontiers cautiously, using mathematics, observation, and experiment to navigate the unknown. Observational limits extend to the universe's expansion. Dark energy accelerates space, causing distant galaxies to recede faster than light can traverse the intervening space. These regions are forever beyond our reach, and no signal can bridge the gap. The universe has effectively isolated parts of itself from observation, creating permanent horizons. In these regions, we cannot measure, interact, or even infer details with certainty. The edges of knowledge are therefore dictated not by our instruments, but by the universe itself. Space-time and expansion define where science can operate, producing boundaries that are both absolute and elusive. Even in regions we can observe, unseen forces dominate. Dark matter shapes galactic rotation curves and the cosmic web, while dark energy drives accelerated expansion. These components constitute over 95% of the universe's content, yet remain largely invisible. Our perception, even aided by instruments, captures only a fraction of reality. Understanding requires indirect inference, modeling, and experimentation, linking observable effects to the unseen causes. Science interprets signals, reconstructs structures, and tests predictions. But we are always peering through a veil, glimpsing the universe in fragments, patterns, and shadows. Technology expands these observational limits. Telescopes like Hubble and James Webb peer deeper into space than ever before, revealing the first galaxies, primordial star clusters, and faint cosmic structures. Multi-messenger astronomy combines light, gravitational waves, neutrinos, and cosmic rays, integrating information across different carriers. Computational models simulate galaxy formation, dark matter distribution, and cosmic evolution, allowing humans to predict structures beyond observational reach. Quantum sensors, precision interferometry, and high-energy detectors extend experiments to extreme scales, probing the foundations of reality itself. Each advancement reveals the universe more fully, yet simultaneously exposes new horizons beyond comprehension. Experimental limits are similarly profound. Observing black hole interiors, quantum gravity effects, or cosmic phenomena at singularities is impossible with current physics. We can measure surrounding effects, accretion disks, relativistic jets, gravitational lensing, but the internal mechanisms remain inaccessible. Entropy, event horizons, and quantum uncertainty impose fundamental boundaries on knowledge. Experiments push to the edge of these limits, testing theories and exploring extreme conditions. Yet some aspects of the universe may always remain beyond direct experience. Science advances by probing these boundaries, turning limits into questions, and questions into new frontiers of knowledge. Even our understanding of space and time itself is bounded. The universe may have dimensions beyond the 3 spatial and 1 temporal dimension we perceive. Extra dimensions, if they exist, are hidden from direct observation, potentially influencing forces, particle interactions, and cosmic structure. Cosmic expansion, quantum fluctuations, and gravitational effects may all carry signatures of higher dimensions, yet detecting and interpreting them remains a formidable challenge. Human comprehension must therefore reconcile the observable, measurable universe with the possibility of hidden layers and unseen structures that define reality on scales beyond direct perception. In considering life, matter, and energy at cosmic extremes, we confront further boundaries. The observable universe presents familiar conditions: stars, planets, and galaxies composed of baryonic matter. Beyond this, extreme radiation, near absolute zero temperatures, high-energy cosmic events, and the influence of dark components define regions hostile to life as we know it. We can model behavior at these extremes, but direct interaction is impossible. Human understanding must therefore combine observation, theory, and experiment to explore realms that remain physically unreachable, using proxies and simulations to illuminate the cosmic frontier. The question of cosmic edges, horizons, and boundaries ties directly into the limits of understanding. Observationally, the speed of light and expansion define horizons beyond which direct perception is impossible. Experimentally, quantum mechanics, relativity, and extreme energy physics define boundaries where theories may fail or diverge. Computationally, simulations extend human reach, yet they depend on assumptions and models grounded in local observation. Together, these limits frame what it means to know the universe, highlighting that understanding is always partial, provisional, and evolving. Despite these boundaries, the human drive to explore persists. Future missions, advanced telescopes, quantum experiments, and gravitational wave observatories promise to extend the edge of knowledge, revealing previously hidden regions, forces, and phenomena. Observations of the first stars, mapping the cosmic web, detecting primordial gravitational waves, and probing quantum behavior at extreme scales all push the frontier outward. Each discovery illuminates not just distant structures, but the rules and forces that govern the universe itself. Science advances by navigating limits, probing edges, and integrating data across scales, creating a richer and more detailed map of reality. The edge of human understanding is also defined by the interplay of observation and theory. Observations suggest structures, forces, and behaviour. Theories interpret, predict, and extrapolate. This synergy allows knowledge to extend beyond direct perception, enabling reconstruction of cosmic history, the modelling of galaxy formation, and the testing of physical laws under extreme conditions. Even as we approach observational or experimental boundaries, theory illuminates possible realities, guiding future exploration and suggesting new frontiers. At the larger scales, the universe itself presents a dynamic and evolving boundary. Expansion, acceleration, dark energy, and dark matter shape the cosmic horizon, defining the limits of interaction. Quantum fluctuations seeded the earliest structures, yet remain hidden at small scales. Singularities, black holes, and extreme events define localized edges where current physics breaks down. Understanding these boundaries is central to probing the universe, testing the foundations of space-time, and exploring the interface between the observable and the hidden. Human understanding is ultimately a cumulative and iterative process. Observations refine models, experiments test predictions, and simulations extend reach. Each frontier conquered reveals new horizons, and every limit encountered challenges assumptions. Science advances not by reaching a final edge, but by exploring successive boundaries, translating observation into understanding, and illuminating realms that were previously inaccessible. The universe remains both a challenge and a guide, expanding faster than our perception, yet revealing patterns, principles, and structures that can be measured, tested, and understood. The edge is not merely a physical location, it is a frontier of knowledge, a space where curiosity meets limitation. Telescopes, gravitational wave observatories, quantum experiments, and simulations illuminate what exists, how it behaves, and how it interacts. Observation captures snapshots, gravitational waves reveal dynamics, and quantum studies probe the underlying rules. Together, they provide a multidimensional approach to understanding the cosmos at its boundaries. Science teaches that the edge is both real and illusory. Observational limits, causal horizons, and quantum uncertainty define boundaries for measurement. Yet existence continues beyond these limits. Galaxies, dark matter, dark energy, and possibly other universes remain, beyond perception, but real. Human understanding navigates this paradox, translating limited data into knowledge, creating models, and pushing the frontier ever outward. The edge of the universe is mirrored by the edge of comprehension, both vast, complex, and humbling. The universe as a frontier invites both awe and curiosity. Every new discovery, from distant galaxies to quantum fluctuations, challenges perception, expands understanding, and illuminates previously hidden structures. Future exploration, telescopes, gravitational waves, quantum experiments, and multi-messenger observations promises to reveal more of the cosmos, pushing human knowledge to regions currently beyond reach. The universe is a canvas of unimaginable scale, complexity, and mystery, where each edge encountered marks not an end, but an invitation to explore further. Are we really at the edge, or is it just the beginning? The question resonates not because we know the answer, but because the universe continues to expand, evolve, and reveal itself in ways that challenge perception. Human understanding is bounded, but each boundary is a frontier, a space for discovery, measurement, and insight. The cosmos is vast, layered, and dynamic, and every limit we encounter opens the possibility for new exploration. Reality extends far beyond perception, inviting us to push, probe, and imagine the vast reaches that lie beyond sight. The edge of human understanding and the edge of the universe are intertwined. Observation, Experimentation and theory illuminate regions within reach, while cosmic expansion, quantum uncertainty, and hidden energy structures define limits. Together, they create a vision of a universe that is vast, dynamic, and filled with phenomena beyond direct perception. Science does not merely map what exists, it defines what is knowable, reveals patterns, and challenges the assumptions of reality. Each horizon approached is both a boundary and an invitation, a frontier where curiosity meets the immense, unseen, and unknowable universe.